Hola, hola, hola. Hola, hola.
Sí.
¿Se escucha?
Sí, bueno.
¿Se escucha? Sí, me dice ponémelo.
Capaz que me apaguen la música, ¿no? Marce, ¿se pueden apagar la música? Ah, ya está. No digo eso. Hello. Hi. Hello. Hola. Good morning, everyone, and welcome to Khipu 2023. So, my name is Pablo Sprechmann, and I'm speaking on behalf of the Khipu Organizing Committee. We are truly delighted to see you all here once again in person after 4 years. It's been a long wait, but we're very happy to be here, and we are all looking forward to this amazing week of learning and collaborating among us. So, before we start, I wanted to take a short moment to talk about the general idea of Khipu, as well as sharing important information about the week. All right, so the goals of Khipu are to offer advanced training in machine learning and AI for our region. We want to strengthen the machine learning community in Latin America, which means promoting collaborating within researchers in the region. So the goal is to talk to each other, get to know each other, and as well as facilitating connection and knowledge exchange with the international community. We also want to grow awareness about the use of AI and how it can benefit Latin America and the world. All right, so as many of you know, Khipus are these really awesome devices for recording information. They were used by many cultures in the Andes, and the idea is that they were used for storing knowledge as well as communication. We do have a Khipu here. Actually, we're going to put it in the podium in a few minutes. Thanks to Omar Flores, who's sitting over there. He brought us a real Khipu from a village close to Cusco. And the tradition is we're going to hang it here. You should come and see it during some of the breaks. It's really cool. So to honor our heritage, we chose this name for our event. So this is our third event. Many of you were here in 2019, where we had our first in-person event. Then, during the pandemic, we could not see each other, so we had this event series in AI online. Many of you have participated. And so now we come back to in person, again in Montevideo. Okay. There you go. So we want to thank our sponsors. They are the ones that make this possible. So next door we have the sponsors booth that you are going to see the awesome things that they do and learn about the opportunities they have. Particularly, we want to thank Facultad de Ingeniería. This is the house to many of us and the place where we are being hosted. So we have now the honor to have Maria Simón, the Dean of Facultad de Ingeniería, and she will give some brief welcoming words to all of you. Please welcome her.
Thank you, Pablo. Thank you all for being here. On behalf of the Facultad de Ingeniería of the University of the Republic, which is a public university in Uruguay that has many sites in the country, we are here in Montevideo, and on behalf of the faculty, it is for me a honor and a joy to welcome you, to give you our warmest welcome, and to wish you have a nice time here with us. We are very happy to meet every friend again, old friends and new friends, after a period of isolation that was very hard for us. That was very hard maybe for everybody, but has a strong impact on learning, on meeting, on research. But on the other side, we paid very much attention to data science because of the pandemic, to machine learning and artificial intelligence in order to improve our lives and to fight against this real emergency. Now we are here again. This is the second or the third, the second presidential Khipu, and we are really very happy of having you here and to host this meeting. Repeating a meeting is also very important, but it is becoming a habit. People prepare the next Khipu, and it is for us, as I said, really a joy to have you here. I want to recognize the work of the organizers. Organizing a local event is very difficult. It is a lot of work, but it is also a happy event. It is an opportunity for our teachers, for our assistants, for our students, for Uruguayan people in general to have this meeting here in Uruguay. Thank you, and I wish you a very good time with us.
Thank you very much, Maria, for your kind words. So now we are going to share a little bit of information about how the week will go. So we have an amazing lineup of really top international world experts from the region as well as the international community here to share their knowledge and talk to us. So we are going to have lectures and research talks that will happen in this, our main auditorium. During lunchtime, Khipu will provide lunch, which I'm going to tell you now where it's going to be. Today and tomorrow, during the lunch break, we're going to have posters. I don't know if you saw, but there's available in the webpage the list of titles and abstracts. Really cool works. I'm looking forward to it. So that will happen today and tomorrow during lunchtime. And then in the afternoons, Monday through Wednesday, we're going to have practical sessions. Thursday and Friday mornings, we'll have parallel sessions, one in the main auditorium and the other one in a room upstairs here in this same building. We're going to have 2 events that will happen outside of this place, and I'm going to talk to you in detail in a second about them, which are the Women in AI event Thursday night, as well as the closing event on Friday. There we go. So this is a satellite image of where you are. You are you see here, we are here in the bottom. That's the main auditorium. On top of it is where the poster sessions and the sponsor booths are. That's next door, in the room next door. And then lunch will be across the street, this little pedestrian street where you came on. Across the street, that's where we are going to be giving lunch boxes. So then, in order to go to the practical sessions, that will be in the main building of Facultad de Ingeniería, floors 312, 314, and then 401 and 402. You're going to have to walk next to this little football pitch. This is Uruguay, so it's full of football pitches everywhere. So you're going to walk there, and that's where it's going to be. We're going to be sharing this information, and in the booklet that you received during the registration, you're going to be able to see this information. All right. Sorry about this. Okay, the Women in AI event will happen at Kibon. We're going to start 7:30 sharp with a very nice panel. Then there's going to be a nice dinner, music. It's going to be very cool. Buses will leave from the Dassler Hotel starting at 6:30. And please RSVP. We have shared with you a link to do that, because if someone cannot make it, we're going to try to use that space for someone else. And then, one more. Okay, this is not very... I'll take that. There we go. So the last closing event will be at beautiful Teatro Solís in the city center. And we're going to have really cool TED-like talks, some keynotes, as well as roundtable. Again, here, please RSVP. We're going to leave at 1 p.m. from here on Friday and take buses to go over there. All right, and with this, we're going to go for, so the current day, and I'm really sorry, Luciana, we took some time. We're fashionably late as the last time. It's important to keep traditions. So we're going to start with this Machine Learning Fundamentals talk by Luciana Ferrer. Then we're going to have some spotlight talks by Mónica Tentori as well as Rodrigo Nogueira. After the break, Joan Bruna will come to speak about deep learning fundamentals, and then we're going to have a second round of spotlight talks by Diego Galeano and Gabriela Magitman. Then after the lunch, we're going to have the poster session next door, and Jorge Sanchez will take the lecture on computer vision. After this, we're going to have some sponsored talks by Ceibal, Germán Capdeurat will talk, Meta Matías Tassano, and Adme Ruben Chaer. Then after the break, we're going to have the first research talks of the week, Guillermo Sapiro and Marco Couturi. Finally, we'll have these 2 practicals. You'll have to choose between the 2. One is building ML in an open, collaborative way with Hugging Face ecosystem, and then there's going to be another one teaching JAX, Optax, Haiku, and CNNs. So really welcome again to this event. We're very, very happy to have you here. And I'm going to give it now to Enzo Ferrante, who will introduce our first speaker. Welcome.
Thank you very much, Pablo. So, hello everyone. I'm really happy that this is happening again, and we'll have, again, as same year, Luciana Ferrer as first speaker of the day. So, Luciana Ferrer, she received her BS degree from the University of Buenos Aires, Argentina, in 2001, and her PhD degree from Stanford University in 2009. She is a researcher at the Computer Science Institute from CONICET in Argentina and University of Buenos Aires. Prior to her current position, Luciana worked at Speech Technology and Research Laboratory, SRI International, USA. And her current research interests include speaker and language identification, mental state detection, and pronunciation scoring for second language learning. So with that, are you ready, Luciana? It worked before, so it will work now, we guess.
Antes funcionó inmediatamente. Ahí va, ¿no? Lo probé hace un rato. Era ese. Ahí va. Bien, gracias. Dale. Okay, so let's get started because we are on a clock. I won't be able to reduce the time, so somebody will have to pay for the delay, not me. Okay, so does this work? No. Okay, so the talk today will be about how to best use and evaluate the output of probabilistic classifiers. So to that end, I'll start by showing what it means, what probabilistic classifiers are. You all know about it, I'm sure, even if you don't use that name for it. Then I'll show how to make optimal decisions using the output of these classifiers, how to measure their performance, and how to decompose their performance into two components, discrimination and calibration. And there's a lot more detail on everything I'll say today in this archive paper. Okay, so the goal of classification systems, as probably all of you know, is to estimate the class of a certain sample. The class here in this talk will be taken as an integer between 1 and n. The usual pipeline for these systems is to divide them into two stages. Basically, the first stage outputs a set of scores for each input sample, one score for each class. And then there's a decision module that makes the final decision, the hard decision, based on these soft scores from the classifier. And what probabilistic classifiers are the subcase in which these scores, do you see that? Not very well. So these scores are posterior probabilities, so given by this expression, the posterior of the class I given the input sample. So that's all probabilistic classifiers are. It's the usual kind of classifier that we use in most papers nowadays. Okay, so the way we make decisions in most of the literature for the binary case is the following. So we have two scores that come out of the classifier, but they are redundant because Q1 plus Q2 is actually only optimal in some situations. Okay, so that's what we usually do in the literature. What I'll explain now, it's a more general approach that actually has some of the special cases are the ones we do. The RMAX is one special case, which is called Bayes decision theory. And to come to how to make Bayes decisions, we actually need to have an objective function. And that objective function is given by these m different possible make the decision of whether this patient has a tumor or does not have a tumor. And in this toy example that I made up, this is not a real example, I decided that it was more expensive, more costly, for the system to decide that a patient doesn't have a tumor when they actually do than the other way around, right? So if the system doesn't make a mistake, of course the cost is 0. If they do, they are different, and to treat a patient that does home, or if you're uncertain, do more tests. And here in this example, I put a higher cost for sending a patient home that does have a tumor than for doing surgery on a patient that doesn't have a tumor. Maybe that's not correct. Maybe it should be the other way around, but I'm not a doctor. But this is more or less the order of magnitude that you would think costs should have. And then the option of doing more tests is actually a lot less costly, but it doesn't have cost of 0, right? Because you're, for example, you are making the patient wait for their treatment. They are going through tests. And if they didn't have a tumor, those are even unnecessary tests. So that's why here the cost is larger than here, right? So we'll come back to this example once we know how to make base decisions and see how the decisions turn out. Okay, so the cost matrix gives you a cost for each sample. Now we need a metric, which is actually something that is across a whole data set, right? So the metric that we define is the expectation of this cost matrix over the test data. And in practice, we actually just take the average, so the expectation of the empirical distribution in your test data. And the expression is very simple. It's actually a double sum over classes and decisions of the cost corresponding to that combination of I and j times the number of samples for that combination. So basically, this is just the average Cij over all your data. And your data set has k samples, right? So now, I didn't say anything about the values that the Cij's can take yet, because they actually could be negative. But in practice, we actually always take them to be non-negative and force them to have a 0 at least one element, one column for each row. So there will be one decision that will have 0 cost. The best decision for every class is the one that will have 0 cost. And the good thing is that having this restriction doesn't take away generality. So we basically can model all our problems with cost matrices of this form. I won't go into the proof, but you can prove that. Okay, so with this restriction, actually you know that the EC is always positive because the costs are positive. But it can still take any non-negative value. So it can take very large or very small values depending on how you choose the Cs. And this makes it hard to interpret. So if you give a C, an expected cost of 500 to somebody, they won't know if that's a large value or a small value. They won't be able to understand if the system is good or bad. So to fix that, what we do is normalize the EC by the value of EC of the best naive system. A naive system is one that doesn't have access to your input samples, doesn't know anything about the samples. It only knows about the priors in your data. And with that, it has to make the best decision possible. So the EC of that system is this one, is basically the minimum expected cost when you plug in the priors to take the expectation. So you choose the decision that will give you that minimum expected cost. And that's the naive EC. And if you normalize your EC with that value, that naive EC, then you know that this normalized EC should never be larger than 1. Because if it's larger than 1, then it means your system is useless. You better just take the priors and make the best decision, always the same best decision, and ignore your inputs, right? So it's a really great reference to have, or so you either normalize or take this naive EC as reference to compare. Cases of the EC, which are very common in the literature. One of them is when the decisions and the classes are the same, so when the columns and rows mean the same thing in the cost matrix. And the costs are like this. So you have zero cost for the diagonal, meaning that 98% by that knowledge that really you're not that far away from the naive system. Okay, so another special case is this balanced error, where instead of taking the 0-1 cost matrix, you set the cost to be inversely proportional to the prior. And in that case, if you plug that in the expression for the EC, you get this, which looks messy, but it's not. It's basically an average of rate for class I, and then you average all of that, and you have what's called the balanced error. And that's the same as 1 minus balanced accuracy, which is also a very common metric in the literature. So basically, these two are special cases of the EC. And here, the naive EC and the naive balanced accuracy is 1 over n, the number of classes. Okay, so here goes a rant on the F beta. So the EC is a very general, flexible metric for classification systems. There's a whole lot of other metrics in the literature being used for special scenarios in which people think that the accuracy is not a good metric, and it's not. So one of these cases is the scenario in which the minority class is the most important one, which is a common case in medicine, for example. You want to detect a rare disease. That is what you really don't want to miss, but it's the minority class in your data. So the accuracy is really bad there because the performance on that minority class is actually washed out by the majority class. So that to me seems completely unreasonable. So you should not favor or penalize a system for deciding more of something, regardless of whether those are errors or not. The error rates for that system are actually here in the EC. What this is doing, I don't know. It doesn't make sense to me. So basically, the consequence of that is that you can have F beta values that are reasonable. They have, say, 0.6, 0.65, 0.7, and you say, fine, it's not a great system, but it's also not horrible. That if you compute the normalized EC, they're actually larger than 1. So it is a useless system, but the F beta doesn't tell you that. You won't know that you have a useless system unless you measure the normalized EC. So my point, I guess, is that if you are in a scenario like this, where the minority class is what matters to you, that's basically in equation what the phrase here says. You will make the best decision J that minimizes this expected cost here with respect to this distribution that the system gives you. If you do that for every sample, then you are also minimizing the expected cost across the whole data set. The caveat here is that in practice, these base decisions may actually not be optimal because you won't take the expectation with respect to Q. When you go to your data set, you compute the expected cost with the empirical distribution, the average, basically. And if that empirical distribution doesn't coincide with the distribution that the system gave you, then something could go wrong there, and the decisions that you thought were optimal may not be. So we will say that when that happens, it's because the Qs are miscalibrated. That will be our definition of miscalibration, and we'll come back to that later in the talk. So let's go back. Let me drink some water. Let's go back to the example with these 3 decisions here of the image of the brain and see what the base decisions are for this example. So we can draw this expression here, the expected cost for one specific decision, J, as a function of Q1, which is the output of the system for the probability of tumor, right? So you have 3 curves, one for each possible decision. And what we see here, for example, is that the cost of deciding to send the patient home actually increases with Q. And the opposite happens with the decision of operating the patient, right? the more likely the patient is that they have a tumor, then if we have a sample with the Q1 very close to 0, what decision should we make? That's the question. What is the decision module supposed to do? And here we see that in this edge here, there's a tiny region where the green curve is below all the others. So that is where you would decide to send the patient home, which is the corresponding decision, right? Only when Q is very, very small, you would decide to send the patient home. And only when Q is very, very large, you would decide to operate. You barely see it there, but there's a small region where the blue curve is below the others. This is not a badly designed example. I did it on purpose to show something that I thought is reasonable, which is only if the classifier is extremely sure about its everywhere else, you would do more tests, right? It seems totally reasonable. Okay, so let's see two special cases of Bayes decision theory that are very common. One is the standard binary case. When I say standard, I mean columns and rows mean the same thing. But the two classes may have different cost. So it's standard, but not so much, because this is not usually considered. The costs are usually considered equal. So, but in that case, if you plug this into Bayes decision theory, you get this expression. You decide 1 if this is satisfied, otherwise you decide 2. And this is reduced to this other expression. If you plug here 1 minus Q, you get this new expression, very simple, that says decide class 1 if Q1 is larger than this threshold, which is an expression of the costs. So basically, we have the same thing that in that first slide or second, but now we have a theoretical threshold. We don't need to tune the threshold. We know what the threshold should be. The true class. So basically, Bayes decisions, which are these dB, which have this expression, which is the same one I showed before, but with the matrix here with the cost function, the more general form where D can be anything, non-categorical. So after you've made your best decisions here, you plug those in the cost, again, the same one that you use to define the best Bayes decisions, and what you get out is called the PSR. It's a cost over the Qs that is tied to the C that you use to define it, right? So this PSR is actually the cost for a single sample. As we did for the EC, you then take the expectation over your data to get a metric. And what that metric, which we will call EPSRs, provides a principal way to measure the quality of the posteriors. It basically assumes you will be making the best decisions possible and then measures the quality of those best decisions. When decisions are categorical, as I said, the cost is basically the cost matrix, and we will call that EC of Bayes decisions, so ECB. That's a metric that basically measures the quality of the posteriors for one specific cost matrix. So one specific application or decision regions. This is actually not enough to measure the quality of the posteriors across the whole simplex, because it's focusing only on one set of decision regions. If you are planning to change your cost matrix, or if you want interpretable posteriors, then that's not enough. Luckily, because we let D be non-categorical if we want, we have a whole family of EPSRs that we can define for those other cases where D is not categorical. And that lets us define EPSRs that are actually measuring the performance of the posteriors more exhaustively across the whole simplex. And one such metric is a very familiar cross entropy. So if we define the PSR to be the negative logarithm of the Q of the true class, and then you take the average of that, you get the cross entropy. So the cross entropy is basically one case of unexpected, because you could replace it with the priors, and your normalized cross entropy would be 1. Larger than 1 means worse than that. So you should throw away your system and just use your posteriors. Okay, so a great property of the cross entropy is that it's an integral over a family of ECBs. ECB, remember, is the EC of base decisions. So we'll see an illustration for the binary case, but we can do the same for the multi-class case. So here's the cost matrix parameterized by one parameter t, which goes between 0 and 1. Right? So this is a family of cost matrices, one value for each value of t. Now, I simulated some data set, and I simulated a system to classify that data. And then I computed the ECB value for each value of t for that data set, right? So for each t, you have a base threshold. You use it to make categorical decisions, and then you measure the EC for that same value of t. And you can do that for every t and get a curve. So that's one system run on one specific data set, simulated in this case. Now I simulated another system, and I got this other curve. Here, the point where t is 0.5, the cost matrix has the same cost, so this is the accuracy, or I think actually proportional to the accuracy. So these two systems, I generated them on purpose so that they would coincide at the accuracy. Basically, they have the same accuracy, but they're very different from each other. You can see it. At any other t, the systems are not the same. If you only measure accuracy, then you would think these two systems are identical. You could choose any of them, but they're not, right? So what cross entropy is telling us is the integral over this whole curve for each system. So if you were to measure the cross entropy, then you would see that one system is better than the other. Okay, so basically the cross entropy, instead of committing to a single cost matrix, like the EC, it actually integrates over all of them. And it gives you an exhaustive measure of how good your posteriors are. Now here's an example of a true example from a paper from 2017 that is very highly cited, that raised awareness on this issue that modern DNNs are having, which is that they overfit the cross entropy. So basically what this is showing is the test error, 1 minus accuracy, and the test cross entropy as a function of the training epoch. So at the beginning, both metrics come down at the same time. This is nice. But then they change the learning rate, that's why it falls suddenly, and the cross entropy starts to grow. And then they change it again, and both come down, but then the cross entropy starts to grow again, and the accuracy does not. So if you were monitoring only accuracy, you would choose this model, the one with the lowest accuracy. But that model actually has a worse cross entropy than you could have had here, right? So depending on your purpose for that system, you may choose a different epoch. What seems to be happening here is that these DNNs that are very large and have lots of parameters, and you train them with lots of data, they tend to overfit the cross entropy more easily than the accuracy. So you would stop at different places depending on what metric you care about. The good news is that you can actually stop here and fix your posteriors and have the best of both worlds by doing calibration, which we'll see next. So before going to calibration, let's summarize this last part. So EPSRs are a principal way to evaluate the quality of the posteriors. The principle is you will make rational decisions. You will do the best you can to optimize your EC, and that is base decision theory. So if you assume that you're a rational being and you will make the best decisions possible, then you do that and you measure how well you do. And that's EPSRs. That's what EPSRs do. And there's two very standard EPSRs in the literature, even if they are usually not called that. One of them is the accuracy of the argmax decisions. I showed you that the accuracy is one particular EC, and that the base decisions for it are the argmax decisions, right? So this is one EPSR that evaluates the posteriors at one specific operating point for the 0-1 cost matrix. The cross entropy, on the other hand, evaluates the performance of the posteriors across the whole simplex. So it's a more exhaustive measure of the performance of the output of the classifier. The mysterious thing to me is that cross entropy is usually only used for training in the literature, very rarely used for evaluation. And Martin is, yeah, it's much more rare than accuracy. But it's actually a great metric for evaluation. So my suggestion is if you care about the quality of the posteriors, use it also for evaluation, not just for training. Okay, so we go to calibration. So the usual definition of calibration is that the posteriors are calibrated if they satisfy this equality here. So the Q for class I should be the posterior of class I given the whole Q, the complete vector, right? This seems like a recursive definition, but it's not. It actually, intuitively, it means that if you have a data set and you select the samples for which the system told you that QI is, say, 0.8, from those samples, you would expect 0.8 of them to be of class I. That's the intuition behind this equality here. In the weather forecasting example, which is basically the task for which calibration was first studied decades ago, you would say that to trust a forecaster, you would expect that it rains X% of the days, say 80% of the days that the forecaster said that the chance of rain was 80%. That's what you expect from a good forecaster, right? Now, the problem with this definition is that it relies on this P, which is supposed to be the true P, the underlying P in your data. And the problem with that is that we will never have access to that P. Your data doesn't come with the P. It comes with the categorical class. In the best case, when you have labeled data, you have the labels. You don't have the posterior. So you will never have access to this reference here with which to compare. So this is the definition, which is intuitive but useless. So we have a more practical definition, which is that the posteriors Q are calibrated if the base decisions made with them are optimal. And that's what I mentioned at the beginning. So it circumvents the need for this magical P that we'll never have access to, and it gives us a very practical way to measure the quality of the calibration. So let's look at the simplest example, which is for standard binary classification, where we have this expression for the threshold that I showed before. So this would be optimal if the Qs were calibrated. Now, to know if that's the case or not, in this simple case, you can actually sweep a threshold across all the possible values of Q and choose the one for which the EC is the best. So choose the optimal threshold. And then measure the difference between the EC here and the EC here. If they're different, then it means your system was not calibrated, because otherwise you wouldn't have been able to find a better threshold. That's how we define calibration, right? We say, if you are able to find a better threshold, then your Qs were not calibrated to begin with. They were not the best they could be. Now, we do this in the binary case. In the multi-class case, or when decisions are not the same as the classes, it's a lot messier to actually tweak your decision regions. You see, there's not a single threshold. In that case, you have these things, this line that define the regions. So instead of doing that tweaking of decision regions, we actually transform the space of Qs into a new set of Qs in a way that base decisions are optimal for that new space. So instead of transforming the threshold, you transform the Qs so that this threshold is optimal. You see that these two things are equivalent, right? You could do either in the binary case and in the multi-class case, but the simplest thing is in the multi-class case is to do it to the Qs rather than to the decision regions. So in the general case, we compute this metric, which is the difference between the actual EPSR. By actual, I mean the one that you measure on the output of the system as it is. You take the Qs and you compute, say, the cross entropy on those Qs, on some data set, right? You have a test data set, you run your classifier, compute cross entropy. And then you do something to the Qs, some transformation F, that hopefully, if you've done it well, will reduce your EPSR, your cross entropy. And then you measure again that cross entropy. And you see how different those two cross entropies are before and after you've done your best at optimizing the cross entropy. So the calibrator, what it's doing is basically transforming the Qs so that you improve calibration. And I'm using the word calibration for two different things, right? One is the characteristic of the Qs, and another thing is what you do to the Qs. And that's how it's used in the literature. I'm sorry. It's an overloaded word. But so the F is trained hopefully on held out data, although in the literature it's usually trained on the test data itself. But you see that that is risky, right? Because if you train your F on the test data on which you're actually measuring the cross entropy at the output, then that cross entropy will be optimistic, and your calibration loss will be pessimistic. You will overestimate your calibration loss if you cheat, if you train your F on the test data. But again, that's what most of the literature does anyway. So here's an example of the form that the F can take. This is a very general one, very simple, that works extremely well in most scenarios that I run into. So you first take the logarithm of the Q. This is essential. Or take the logits of your classifier, so before applying the softmax, and transform it by a scalar weight and the vectorial B. So here there's one shift for every class. And you train these two, again, hopefully on held out data, and then you take the softmax to go back to something between 0 and 1, right, to posteriors. So this is a very general expression that works very well, and it's very easy to implement. So you see, you may be thinking, but then the calibration loss actually depends on how I do this F. And yes, that's the case. So we'll never have a ground truth calibration loss. Calibration loss will depend on your best effort for doing calibration. And that's basically intuitively the same that saying, I will never have access to the true P. It's the same reason. You will never have the actual P, and you will never have the true calibration loss. The best you can do is basically do your best job at doing this, the calibration, and get as close as possible to that true calibration loss. Okay, so the nice thing about that expression is that you can turn it into this one, the composition of the actual EPSR, into two terms. So you have one term is the calibration loss, which measures the calibration performance by definition, which is the part of the actual EPSR that you can improve by doing this. So you create a new classifier by concatenating your old classifier with the calibrator that you've already trained to obtain the calibration loss. So you solve the problem of diagnosing calibration and fixing calibration at the same time. So this new classifier here will have calibration loss of 0. You fix that part. Now, you may still have a bad optimal EPSR. So this new classifier may still not be as good as you would want it. And then you're in trouble because you have to go to the classifier to do the best you can. And that's a lot more messy. It requires probably more data or changing the architecture. Fixing calibration is quite easy compared to fixing discrimination. So discrimination is basically the separation between the classes. given your scores. Now, this is very briefly to address the topic of Khipu, which is ethics and fairness. I want to say that in our experience, calibration tends to degrade a lot more severely than discrimination on underrepresented groups. So on data that is minority groups in your training data, you will probably not be able to see you have a problem if you only measure discrimination. If you only measure area under the curve or equal error rate, you won't see that there's an issue on those underrepresented groups. If you measure calibration, then you will. I can say a lot more of that, but I don't have time. So another warning here is that calibration doesn't guarantee that your posteriors are useful. You can have a system that outputs the priors that will be perfectly calibrated, but it will be useless. It doesn't tell you anything about your input samples. It only tells you about the priors. So calibration is not this magical concept. It only tells you that your base decisions are the best they can be according to your best effort at calibrating. But it doesn't tell you that the system is useful. What tells you if the system is useful is the actual EPSR. It's the combination of both things, the cross entropy. Okay, so we have two definitions. Very briefly, I want to say that they're actually the same thing, but you need to formalize a bit more the usual definition to acknowledge that this true P doesn't exist, and you'll never be able to find it. So instead of using a true P, you use a model for P. And then when you do that, you can find the equivalence between the two definitions. Now, I talked about calibration loss as if it was a popular metric, but it's not. It's actually used in some tasks, speaker verification, very heavily. The most heavily used metric for calibration is called ECE, which is defined as this. So if you have a data set for the binary classification case, and you bin the Q once, so you run your system on all your data, you take the Qs, you bin them in bins of 10. And then you measure two things. You measure, gave up on me out there. You measure the average Q1 within each bin. So take this bin, measure the average Q1. It should be more or less 0.85 probably here. And you also measure the fraction of samples of class 1. So if the system is calibrated, you would expect that this Q wiggle, which is basically your calibrated Q, should coincide with the Q bar, which is the mean over that bin, right? That's your goal, and that would happen if the histogram coincided with the diagonal. So all the bars should be in the diagonal if the system is calibrated. Now, with this Q wiggle, you could go to the definition of a calibration loss and compute that. But what ECE does instead is come up with a heuristic for measuring the distance between the bars and the diagonal, which is just the average gap between the bar and the diagonal. Now, this is like the reinventing the wheel and making it hexagonal instead of rounded. There's no reason to come up with a heuristic if you have PSRs. For decades, we've had PSRs. So the problem with this is that it doesn't tell you really how good your posteriors are, because it's not using the very definition of PSRs, which is what they are designed to do, right? So that's one problem. And another probably bigger problem is that when you go to the multi-class case, there's not a natural extension of this approach. So this is called histogram binning, this calibration approach that we did here, this histogram binning. To do that for multi-class case, you can, but it doesn't scale because you have lots of bins, and it's a mess. And it overfits very easily. So you don't do that. What they do is actually map the multi-class case into a binary classification that basically measures only the performance of the highest score, the confidence. So you've basically broken everything, because you're not longer measuring the performance of the whole vector of posteriors, but only of one value, the largest. We can very easily find examples in which this ECE doesn't really measure at all that you have miscalibrated scores. Well, the other thing is that histogram binning is actually not a great calibration method, even for binary classification. There are many better ones. And also that in the usual way of computing ECE, well, the only way of computing ECE is to compute that calibration transformation on the test data itself, which I argued is dangerous because it can overfit. And there's lots of papers showing how ECE is biased. Yeah, because you're cheating. Okay, so I don't know how I'm going on time. 5, okay, good. I'm almost done. So now I've been talking about posteriors, and you may be thinking, oh, crap, I've never mentioned the quality. I've never actually assessed the quality of my posteriors. So should you care about it or not? Here's my opinion. So if you need interpretable outputs, then you probably are already measuring the quality of your posteriors, probably using ECE. And my suggestion here would be drop the ECE and start using cross-entropy. Cross-entropy is really all you need. Or you can use Breer score, which is another EPSR. That's really what you want, right? The overall performance of your posteriors. Now, if you still have the chance of improving your system, of adding a calibration stage, then go ahead and also estimate the calibration loss with some calibration approach. If you happen to find the calibration loss is large, then you have a very cheap gain in your hands. You just add that calibration stage and improve your system very, very easily. So that's the case where you need interpretable outputs. If you do not, then the next question is, do you only care about one specific EC? If you do not, if you actually care about a whole family of ECs, because, for example, you're going to hand your system to a set of different clients, and each of them will have a different cost matrix, then you need your posteriors to be good across the board. And to be good across the board, you need to measure cross-entropy again. Now, if you do only care about one particular EC, and you know you'll never use the system for any other operating point, that's all you care about, and you are in the standard binary case, right? Classes are the same as decisions, and you have only 2 classes, then you can do this EC approach where you sweep the threshold and find the best one, and you're done. In that case, you don't care about the quality of your posteriors because you're never going to use them. All you need is the best possible threshold. Now, if you're not in that scenario, if you have multiple classes or the decisions are different from the classes, then, as I said before, it's very hard to tweak the decision regions, which would be the generalization of sweeping the threshold, right? So instead, it's much easier to transform your queues, make sure they are good, and then use Bayes to make your decisions. So the most common instance of this last case is accuracy with argmax, right? And the point here is if you are using this accuracy with argmax, you need to make sure that your posteriors are calibrated because you are relying on that fact. The argmax decisions will only be optimal if the posteriors are calibrated. Now, the truth is that in modern DNNs, they usually are very well calibrated at the accuracy point, not everywhere else, at the accuracy point. So if your priors in training and testing are the same, then you're probably fine. You can get away with not measuring the calibration. But if you suspect that the priors with which the system was trained, or you know that the priors with which the system was trained, for example, you balance your training data, but then your test data is not balanced, the priors are different, then calibration breaks completely. Well, depends on how much the change was. So in that case, if the priors differ, between train and test, then you need to worry about calibration because argmax rule won't be optimal anymore. Okay, so conclusions. EC is the ultimate classification metric for categorical decisions. That's my opinion. We don't need anything else. We don't need F beta, Matthew correlation coefficient, and the million other metrics that are going around in the literature. What you need is to find the right EC for your problem. And this is regardless of how the decisions are made. You don't need to be doing Bayes decision theory, although it's recommendable. But you can make categorical decisions in any way you want and still use EC as a metric. Now, that's if you care about one specific cost matrix. If you want interpretable posteriors or you want to make decisions across a whole range of cost matrices, then you need to use, for example, cross entropy or Brier score, which I didn't mention, but it's another good option. And if you have the chance still to improve your system by doing something to it, then my advice is to do this decomposition into calibration and discrimination and figure out if by adding a calibration stage you can actually get cheap gains out of it. So if discrimination is bad, you're in trouble, you need to go and modify your classifier. If calibration is bad, then it's very easy to solve. So why not try? Okay, so here's some books on Bayes decision theory. And here are some very small selection of papers, but there's a much larger selection in the archive paper that I mentioned before. This is a paper that is currently in change. There will be new versions in the next couple of weeks or months. And there's corresponding code for the paper in this repository, which allows you to compute the EC and make Bayes decisions, and it ties to another repository that does calibration stuff. Okay, thank you. Right on time?
Right on time. Well, thank you very much, Luciana, for this amazing talk. There is some time for questions from the audience. Also, if you are listening us on YouTube, you can post the questions on the chat. We were monitoring it, there were not, but in case there are some, just do it. So, any questions from the audience? If not, okay, there. Yes, just for the YouTube, maybe.
Okay, so thanks for the very nice talk, Luciana. So I was wondering, in cases where you have a very skewed cost matrix, you basically mentioned using it a posteriori to find your decision boundaries. But in those cases, wouldn't you advocate to use it during training as well? So can't you just train your model and optimize it for the cost function that you need at that point? And in that case, I mean, if the data set is well balanced, so you might have a hope of it already being Bayes optimal, right, in that sense?
The problem with the EC is that it's not smooth. So it's very hard to optimize with our current approaches of gradient-based approaches. So what I usually do in those cases, which are very common for us in speaker verification, for example, it's train with a cross entropy that is balanced to those priors that you want. Even if your training data is not, you can artificially change the weights of the cross entropy to be the ones that you want. And that cross entropy will actually be very good for the EC that you want. But it gives you a soft version of the EC. Some people have found or made up versions of the EC that are smooth. I don't see any gain over doing the cross entropy approach.
Okay, thanks.
Right. Is there any other question? There.
Hi, Luciana. Thank you very much for the talk. So I would like to to ask you about the Breer score. What would be the difference with the cross entropy, or is it, what characteristics do they have differently to choose one of those?
So
or how to interpret them?
Yeah. So the PSR that the cross entropy is based on is the negative log loss, which penalizes extreme errors, so basically errors where the Q is 1 for the wrong class, very strongly. So it goes to infinity, basically. So the logarithm, if the Q for the true class is 0, the logarithm is infinity, so your cross entropy will be infinity. So it's a very hard, very strong penalization for that case. Breer doesn't. Breer is maxed out at 1. So that's the maximum cost that it can apply to a bad Q. So if you care about very severe extreme errors in your Qs, then you should probably use cross entropy instead of Breer. Although Breer is very common in the medical literature for some reason, much more than cross entropy. But in that case, I actually think it's even more important to use cross entropy. You don't want to have the probability of tumor be 0 when there was a tumor.
Thank you.
One last question there.
Hi, Luciana. Thank you very much for your presentation. It was really good. I have a question. You know, we usually, when we try to publish a paper, we usually try to evaluate our models in different data sets in the end. And, you know, the prior in every one of these test sets, it's not always the same, especially in medical imaging, where our data sets are usually quite different one another. So my question is, how this calibration affects the generalization to other data sets with different priors. Have you studied that?
Well, yeah, I mean, theoretically, you know that if the priors in your test data are different from the ones you trained on, then calibration will be bad. No matter what you do, it will be bad. So you should probably calibrate for every test data, at least to make sure that the priors are adapted to that data. You can also do it with an expression. The paper has, I think, the expression for fixing it. But the best thing is just if you have some data, held out data for each task, calibrate it, and then you fix that problem. And after you fix the problem, then that's it. You don't need to care about the difference in priors. Did I answer the question?
I think so, yeah. So that explains why we end up calibrating or tuning this transformation for each of the test sets, right?
Yes. So
because in the end,
we are currently tuning a threshold for each data set. It's basically equivalent, but you're not actually ensuring that the posteriors are interpretable. So if you actually care about the posteriors, you need to calibrate the posteriors. You cannot get away with tuning the threshold only.
Such a tough problem.
Yeah.
Thank you very much.
Actually, calibration is not hard if you have data. It's very, very easy to do. Much easier than anything we do on the classifier. Things we do on the classifier are really complicated and take hours or days or months to train. This is just something that you can do with any of these repositories in minutes. You need to have the held out data to both evaluate and train the calibrator.
That's a tough problem.
Yes,
in the end.
I see. But if you have any test data at all, then that's the data you need to use for calibration. If you know you have a problem, then you have data. Mm-hmm. And that data can be used for calibrating. You can do cross-validation if you don't have enough, right?
Okay.
Thank you.
Well, thank you very much, Luciana. We thank again Luciana, and I invite Rodrigo Nogueira, our next speaker. Okay, we'll now have... We'll now have a round of spotlight talks. You know that we have different type of talks. In this case, the idea is to highlight also research done in Latin America. Well, that was also the case of Luciana. But we'll be having a lot of spotlight talks from different countries around Latin America, showing the research our researchers do to also encourage collaborations, interactions during the event. And it's a pleasure to introduce Rodrigo Nogueira, Rodrigo obtained his PhD in computer sciences from New York University, and he was a postdoctoral fellow at the University of Waterloo in Canada. He serves as an adjunct professor at Unicamp in Brazil and consults for multiple companies in the search engine industry. He was a pioneer in the use of transformers for search and is a co-author of the book Pre-trained Transformers for Text Ranking. So Rodrigo, thank you very much.
Thank you. Can you hear me well? All right. So in this talk, I'll be talking about adapting neural models to languages and tasks. There is 2 parts in the talk. Part 1, I'll show some ways to extract knowledge from these large language models for information retrieval tasks. I'll show how this is different from extracting knowledge for NLP tasks in a minute. And in part 2, I'll talk how to adapt these models to other languages such as Portuguese and Spanish. So part 1, I think everybody saw Palm. It's this gigantic model from Google, 500 billion parameters. It has these amazing capabilities like reasoning. I don't have time to go over the text, but if you didn't see it in the paper, I recommend doing so. You give it as input, and before reaching an answer, it can explain its output. It can reason about whatever it was fed into the input. And it can also explain jokes. And people evaluating on the Big Bench benchmark, it has 150 tasks. You can see that it has a performance that is close to human performance on these tasks. This is kind of polemical, I guess. But anyway, we're making progress with these larger models. And I wanted to use them for information retrieval. But here's one problem with information retrieval in comparison to NLP. So suppose you're doing NLP, you have this question answering task or trying to extract some information from a document. You can take this 1-page document, feed into Llama, this latest model from Meta. It will take about 1 second to answer a question from this document using a state-of-the-art 800 GPU. So not bad. But suppose you want to recommend products or books to users in a recommender system, or you want to rank pages like Google does, and you have 100 candidate documents, and you want to feed these 100 candidate documents and estimate their relevancy for a given user query or user profile. It will take about 40 seconds on these single 800. It's starting to get problematic. Or if you want to do some dense retrieval, you take 10 million passages, paragraphs, encode them into dense vectors. This will take about a month on a single 800, so it's kind of prohibitive to using our academic setup. And here's the depiction of a simple search engine pipeline. I don't have time to explain in detail, but we have the inverted index construction. Think of it as a Python dictionary whose keys and values are made such in a way that it's easy to retrieve documents at query time, or think of it as a repository of dense vectors for your dense retriever. There is also some initial retrieval pipeline, and then a re-ranker that is usually expensive, a more expensive neural network that tries to re-rank these documents. And what we do often is to take smaller language models, transformer-based language models such as BERT or MinLM, and using each one of the steps of these pipelines. But when it comes to large language models, this is a very latency critical pipeline. We cannot apply it directly. We have to find other ways. And I will show 2 ways that we can use these large language models as dataset generators for information retrieval tasks. But I think you can also easily adapt them to natural language processing tasks. So the first one that we published last year is called InParse. It stands for Inquisitive Pairs for Search. And the idea is as follows. You take a prompt with 3 examples. A document and a relevant query. A query that that document likely answers to. So we manually craft these 3 examples. And then we take our corpus with millions of documents, millions of passages, and feed as a 4th example so that the language model can generate a relevant query for each one of the documents in our collection. So now we can easily generate millions of queries, relevant queries for documents in our collection, and you can use these pairs of queries and documents as training signal for our dense retrievers, sparse retrievers, re-ranker components. So it's a cheap way to creating synthetic queries, which are kind of expensive in the real world. You have to have a commercial search engine to acquire these types of queries. And here are the results. We are currently in this, there is this beer benchmark. It's made of 18 data sets spanning from legal domain, biomedical. So it's a pretty diverse benchmark. We're currently placed in second place in this benchmark, and we use the imparse to generate these synthetic data to train our retrieval pipeline. So it's now in a way to adapt to each one of these 18 tests of the benchmark in a synthetic way. We only need three examples as input. The second method I'd like to show how to augment our training data sets. It's called XRanker. So the idea here is follows. The motivation is that, as we saw in the previous talk, we use often these categorical labels like true and false to train our classifiers. In information retrieval, we had tons of binary classifiers. And I argue here that these are very poor training signals. Imagine if you have to teach someone a task that you only communicate true and false labels. It's hard to understand what you have to achieve if you only have that as a signal. So the idea is to augment these target labels that we train our classifiers with natural language explanations. And so in the ideal scenario, we take a model, let's say with a query and a passage, and we want our model to estimate if that passage is relevant or not to our query. And if our training data is good, we could also have an explanation that we can train the model to also output an explanation, not only the label, but as well as the explanation. But where can we get those explanations to build our training data set? So that's where large language models come into play again. Via few short prompts, we can give it as input to the model examples of a query, a passage, a label, and an example that we manually crafted. And then our next example is some example that we have from our training data that we let the model to generate automatically an explanation for. And then we train our model. Our model can be a sequence-to-sequence model. We feed as input a query concatenated with the passage and train it to generate the label together with the explanation. And the results we show that in the blue curve is a model trained without explanations, and the green curve is a model trained with explanations. Given the same amount of training examples, provided the synthetic explanations to the model makes it perform better on our retrieval tasks, and I'm sure that we can also apply the same idea to other NLP tasks. Yeah, so part two, how can we adapt these models to other languages? One thing that we notice in the recent literature is multilinguality emerges with self-supervision. By self-supervision here I mean predicting the next word given a sequence of tokens as input to our models. So the way PaLM was trained is a transformer model. We take a gigantic corpus, is mostly documents in English. There is a minority of documents in other languages. And then we train the model to predict the next word of these texts. And in the end, we can evaluate this model in a few-shot manner using some standard question answering data sets, such as tidyQA. It contains nine languages, and its few-shot performance, meaning that it wasn't fine-tuned on the specific tasks, it was only given a few examples in the input. Its performance is close to a multilingual BERT that was fine-tuned on thousands of these examples. This is not the state of the art, but still it's a good performance given that the model was trained on majority of English texts. And in comparison to human performance, there's still a big gap, like 30 points in a few, at least in this data set. And now comes the question, how can we improve the multilinguality capabilities of these models? One might think that let's make this less English-centric, let's make more balanced a multilingual corpus. But I'll argue in some recent experiments that we did, as well as some past ones, this is not the best strategy if you have a corpus with a lot of data in your target language. So our first experiments date back to 2019. It was published in 2020. It's called BERT-Timbal. It's adaptation of BERT pre-trained to Portuguese texts. Compared to multilingual BERT that was pre-trained on 100 languages, our Portuguese specialized model was better in many tests that we evaluated on. Here I only show two of them. And it's a huge success. People are been downloading it a ton from Hugging Face. Is currently ranked 67 on more than 100,000 models available on the repository. And the good thing here is that pre-training took 1 week using TPUs. Thanks to Google for providing us these free TPUs. They continue to do so. In case you don't know, there's this TPU Research Cloud. They give you TPUs for a month. It's equivalent to I believe, 10 800s in terms of total compute. So if you want to go crazy on the compute side, Google can give you 1 month of access. Or if you want to go to cloud and pay for these GPUs, it's gonna cost you $500 US. So it's not a very compute intensive task in comparison to today's standards. The other model that we tried also to fine-tune to pre-train on Portuguese tasks was T5. So we took T5, pre-trained on 3 billion tokens in Portuguese. And then we compared against the multilingual version of T5, which is represented here by this blow curve. In the x-axis is the number of parameters without embeddings of these models. As you can see, as expected, the multilingual model starts to become better as you increase the number of parameters. But then if you look at our Portuguese version of T5, it's much better than MT5 across the smaller scales. And we also did another experiment. We took, how about if we scale these things up even more? It's not super large compared to today's standards, but we took GPT-J with 6 billion parameters. It was English-centric pre-training. Then we fine-tuned it again on Portuguese, and we saw these huge improvements in the 2 data sets, at least 10 data sets we evaluated. And compared to the Bloom multilingual model that was pre-trained on 46 languages, it's even worse than the English-centric GPT-J pre-training. So the point here is that trying to make these models more adapted to the language that you know that you'll be using at inference time pays off later on. So in summary, the first part of the talk, I said how ways to use these large language models as data set generators. Within parse, with only a few examples, we can generate thousands of synthetic examples, and then with XRanker we can augment these labels with explanations, and then it requires fewer training examples to achieve the same amount of accuracy. And then a good thing about using these 2 strategies that now costs are shifted to an offline stage, so it's very important for information retrieval tasks. And in part 2, I argue here that at least for the 6 billion parameter scale, if you have enough training data, you should do these monolingual models, pre-training monolingual models, than go crazy with 100 languages on multilingual ones. And this answers the question, this begs the question, like, will the future have this single oracle model that tries to answer everything, or to have a society of more diverse models, each one is specialized in some subsets of our knowledge? And finally, I just want to make a shout out here. We're currently training 60 billion parameter model Portuguese texts. I'd love to have some collaboration to also train in other languages, for example, Spanish or domain specific. And there's a ton of things that we don't understand well at the moment, like data curation is super important. And please contact me if you wanted to collaborate. And here's the training curve. There's some spikes. It's not easy to train these models, but it's quite nice. Yeah, thank you.
Thank you, Rodrigo, for the talk. So we have time for one question, in case there is. There? Yes. And in the meanwhile, I invite Monica, if you can.
Rodrigo for the talk.
Oh, no, it's not working. Died?
Thank you, Rodrigo, for the talk. So I was wondering for that second point, do you think mixture of experts models have potential for this society of language models for multilingual modeling?
I think that's a good idea, especially also with adapters. Maybe we can put a lot of intermediate layers in between and reshare the same infrastructure that we have running these models. Yeah.
Thank you.
Okay, since we are a bit delayed, we will continue then with the next speaker. So we thank Rodrigo again. Okay, and our next speaker is Monica Tentori. She's a professor in the Computer Science Department of CICSESE lab, where she leads the Veritas lab. She is a member of the steering committee of the Ubiquitous Computing for both the ACM SIG-Chi and ACM SIG-Mobile chapter, a member of the UC Mexus Advisory Subcommittee. She received the Microsoft Research Faculty Fellowship, and her research intersects in ubiquitous computing, AI, and HCI. So thank you very much, Monica.
Thank you. So hello, I'm Monica. I'm very excited to be here, and I'm not only excited because Montevideo, it's an awesome place to be and talk about my research, but actually because this conference has this awesome emphasis on Latin America, and I think we need such spaces for us to get together and move forward and brainstorm on potential ways of collaborating. So thank you for the organizing committee for putting together this conference. So I'm going to talk a little bit more about me and where I come from. So I'm a professor in computer science in CICSESE. CICSESE is a research center that is located in Ensenada, Mexico. Ensenada, it is like 1.5 hours driving distance from San Diego, California, United States. So we get to go to Disneyland very often. The research areas, so although I will talk more about HCI and UBICOM right now, so it's a very kind of traditional computer science department. So we have parallel computer vision, bioinformatics, algorithms, and data science and information retrieval. So if you want to talk about that with me, that will be okay as well. An interesting thing to highlight about our program, we only have graduate programs in CICSESE, so it's mostly research focused. And but the good thing is that all students that get into this program have full-time scholarships. So it's a very competitive program, so it's hard to get in, but once you are in, you get covered financially for up to 6 years. So my research intersects HCI, UBICOM, and AI. And so I'm part of a lot of communities. And right now, I am in the steering committee of UBICOM, and that works with the SIG-Chi and SIG-Mobile chapters from ACM. And we organize basically this annual conference called Ubiquitous Computing and ISWIC. And it's going to happen for the first time in Latin America. So this is a huge opportunity for, so basically this community, what is asking for Latin American researchers to come to UBICOM and to actively engage into this community. So this is like an open invite, and I think the AI or the type of things that you're doing here are very relevant for this community. I'm going to highlight some of the programs that we have right now. So right now, the SV program, you can scan it there. It's open, so you can register, and we have student travel grants for you to come to Cancun. So hopefully I can see you all there. The other thing is that my research is highly interdisciplinary, so I also get to collaborate and interact with a lot of communities that do not necessarily have to do with technology, but I've been involved in several networks. And one example of those networks is this Sirius network, that the idea is so the University of California in Irvine downloaded a huge amount of money from the Robert Wood Johnson Foundation to support partnerships between the collaboration institutions that you see on the map to create projects together that support accessibility in education, or Accessible F. So this is funded for 5 years, but the idea is to have another fund, which is the LEAF fund, to actually move the research results into industry or partnership with new companies or creating new companies or existing ones, and then replenish, the revenue of all this money into series and kind of create a new model for financial support instead of, us going back into traditional agencies for money and to support the research. So I'm very excited about that too. Because when you work, and what I want to emphasize with this series network is that when you do interdisciplinary research, amazing thing happens, and not only comes with money and this community, but also you get to see how your research that you're doing kind of affect change in the real world. So I really think that the future of AI is human-centered. And I think we really need inspiring stories about how AI can make our world a real better place. So right now I'm going to focus on moving to my research part. So I've been studying like kind of 2 use cases with human-centered AI. And so the last case, I'm not talking much about that, but it's the one that's starting. We are very interested in the series network about using AI tutors for reading and to support vulnerable populations. I'm going to focus more the rest of my talk on healthcare. So digital markers are a very important thing for us to explore and a very difficult to uncover. They are very relevant for us to develop treatments and to diagnose early, especially for those diseases that are difficult to diagnose. And the problem with finding digital markers is that some patterns of diseases or disorders are very erratic. Like take, for example, COVID. And one of other disorders that is kind of like that is autism. So we don't know the biological markers of this disorder, and we don't know either the digital markers. So there's been some research related to visual and vocalization and so those digital markers, but there's an untapped potential for sensory processing disorders, even though 90% of children with autism have 90% sensory processing disorders related to tactile processing. Self-processing. So there's an untapped potential to explore how haptic technology can measure alterations in tactile processing and using these haptic interfaces. So I'm sorry I don't have audio here. So the first problem that we encounter is that there are not a lot of haptic interfaces out there. So we needed to design and develop one. So we use user-centered design techniques to develop what you're seeing in the video, which is a spandex fabric that makes music when children touches, pinches, or interacts with the fabric. And it has games that have challenges related to rhythm and strength. So during the pilot studies on trying to test the efficacy of using bendable sound as a treatment tool for autism, we found out that children with autism in comparison with neurotypicals interact differently with this fabric. And so we wanted to explore more actively what were those differences. So we conducted another study with several children with autism and neurotypicals, and we saw how they performed with this fabric. And we found out that children with autism use less force, so these are more the dominant features that we uncover. Less force, perform smaller gestures, and need more time to complete the gestures, as you can see in the image. And we also use this to classify the gestures with a precision of 97%. So what we learn is that the force is a digital marker of autism, and of course there was another paper in Scientific Reports in Nature that also claimed that force was kind of like this motor signature of autism. But what's very interesting here is that in contrast with this study, we found out that children with autism use less force in contradiction to this, and we thought that because of the affordances of the fabric, this study was conducted with rigid interfaces, so the affordances was kind of different, and this feedback, haptic feedback when interacting with the fabric played a major role. So we wanted to explore more actively this role of this haptic feedback. So we ask ourselves, can the active manipulation of vibrotactile patterns uncover non-digital markers in autism? So we ended up developing this mobile app we call Feel and Touch that runs in mobile rigid displays. And this is a mobile haptic game that uses vibrotactile patterns and uses the analogy of a spider that feels the vibration in their legs. And whenever you tap, or the goal of the game is to tap and do some gestures and create the web and then feed the spider with the box in the game. So we associated each of these gestures to, you can feel the vibration, so you will hear it. That's for illustrative purposes. Every time you tap, we will have a ramp vibration with a default intensity, as you can see in the video. And then the second activity was emphasizing the using of the drag gesture. And what you do is you drag the legs of the spider to catch a box. And along with the dragging, it has like this vibrotactile pattern that we call the ramp pattern, which varies in ascending or descending the intensity of the vibration. So we ran a study with 69 neurotypical children and 14 children with autism using Feel and Touch for close to 12 minutes. And we checked for undiagnosed motor, sensory, and autism problems, which is very common in Mexico. And all children completed the activities using Feel and Touch. What we found out is 2 digital markers, new markers that are unknown currently in literature. First, we found out that the amplitude of the vibration when they tap or drag in the rigid surface is higher for children with autism compared to the rest of the populations. The other biomarker or dominant features that we found is that the radius of the gesture of neurotypicals was smaller to the rest of the children. And we trained on machine learning model, and we found out that we can classify the gestures of these individuals with 96% of precision. But what we really wanted to answer here is if the force was the major driver here. And as you can see in the image, it seems that it's not. It seems that it's relevant, but there are other features that are more relevant and that better characterize this population. So what we learned about this project is that it seems that manipulating this vibrotactile feedback actually changed something in your brain and actually change the way you interact with the technology, and exaggerates these differences in the way we interact with the technology. And of course, this is small data sets, and I don't have more time, so there are a lot of implications with working with small data sets. So just the 2 things that I want to learn from me today is these 2 things. So there's a lot of emphasis in AI regarding passive sensing. And I think what my research has been focused more recently is that moving from passive learning into actually gestural interactions. Like, we cannot live without these mobile phones, and the way we tap, the way we interact, says a lot of our behavior. And also AI is so interdisciplinary these days, so the human is super important, and when working and doing interdisciplinary things, awesome things happens, and especially the LATAM context imposes important challenges. And with that, I will close, and I will be happy to take your questions.
Thank you very much, Monica, for the interesting talk. Is there any question? We have time for one here. Yes. It's not working. We can use this one.
So, can you hear me?
Yeah.
So thanks a lot for the talk. It was very interesting, and it really shines the light on the interdisciplinary work with visual artists and UI people working together with psychologists and etc. So I was wondering, now that we can measure these things and know so much about kids now on the web and people, neurodivergent people in general, how do we build safety around these new findings so that it can't be misused by companies that will take advantage of the ways in which neurodivergent people are not safe in the internet, in regards to attention and shopping in general or things like that.
Yeah, I think that's also a very interesting question. There's a lot of ethical, implications in doing this research. And I think the major question here is, what is the incentive for you to share your data, right? And of course, companies have a financial incentive, and that's okay. But I think what we are failing in doing right now is, so what do I gain for me to share the data? So I didn't emphasize that, but the two tools that we developed mimic actually very successful therapeutic interventions. But the thing that you gain is that you are actually doing a therapy while interacting with these sort of games, right? So that's the benefit. And when you are kind of incentivized towards that, then sharing your data for even a major purpose like early detection of autism or appropriate screening tools development, it's a huge incentive. So I think the question is, what are those incentives? How can you incentivize people and move, distance yourself from, the bad, implications from AI? Yeah.
Thank you very much. Okay, if there are no more questions. No, great. There is one there? No? Okay. So in the interest of time, because we are a bit delayed with the schedule, we will now move to the coffee break, and we'll be back at 10:45. So we'll add 15 minutes more to the break, okay? So thank you very much, and be back in time.
Hello, please take a seat.
Yeah? Good.
All right. Welcome back. While people please take your seat as quickly as possible, we're going to start the next session. So we're going to be having Joan Bruna. He's going to be talking about the deep learning fundamentals. So Joan Bruna is an assistant professor at the Courant Institute in New York University, NYU, in the Department of Computer Science, the Department of Mathematics, and the Center for Data Science. He completed his PhD in 2013 from École Polytechnique in France. He has received many awards. I'm not going to bore you with all of them, but in particular, the NSF Career Award and the Solon Research Fellowship. It would be very hard to list all the things that Joan is interested in and has made contributions on, but just to name a few, Joan has made a pioneering work on the theory of deep learning as well as graph neural networks. So please join me in welcoming Joan Bruna.
Okay. Okay, thank you, Pablo, and thanks for the organizers for inviting me here. I think it's a great initiative, and I'm very happy to visit Montevideo. So Alejandro here, my colleague, gave me like a word of advice before starting, said that I should not try to bore you. So I have an hour speaking, so my goal is really try to entertain you as much as I can. So I'm hoping I'm going to be able to succeed. So really, the title of my talk is the Deep Learning Foundations in the Age of Foundation Models. I don't know how familiar people are with this notion of foundation model. It's really a brand name that Stanford gave to these very large models, for example, language models, right? And these are pretty amazing. I guess by now everyone is familiar with these things. And you know, just as try to calibrate my enthusiasm, right? Like start with this question that is a pretty interesting and suggestive question. I hope that I'm not offending anyone here. I guess I'm in a safe place, right? I guess that Messi and Maradona are probably, you know, favorite than Cristiano, but actually I find that this is actually a pretty good response. In particular, if you focus in this paragraph, that's something that I would probably just coming up with myself, and I would be very proud, right? This is actually a pretty good parallel. So these models are amazing in language. They can also do amazing things with images. As you know, DALL-E you have played. So this is for the context, this is just, these are a bunch of very famous photographs, right? And so we are just, this model is able to actually somehow capture the gist of photographic styles into different people. And, this is, again, something that for anyone working on deep learning for a while, this comes as something that is really surprising. We know that these models, they need to be big in the sense that the more parameters you put them, the better they become, and this is the reality. It is what it is, right? So we have to really, we are in this era where now these models, the more parameters you put them, the better they become. Is everything perfect? Is it, are we completely happy here? Well, obviously, how much do we understand, right? So how much actually these models are solving the problems that we are set to solve? Obviously, this is not always, it's not always perfect, right? And as I guess maybe we are going to hear more about these things this week, when these models are asked to do something that has to do with reasoning, it's not always there, right? So here is like a simple question, if I take two convex functions and I look at the difference, well, we all know that the difference of two convex functions is not always convex. So the model somehow is pretty confident that that's the correct answer. It is the right answer. But once you start looking into the text, well, you start to see mistakes all over the place, right? So somehow, it's starting to kind of mix up completely like the premise. This is wrong, and this is obviously like a wrong example. So somehow we are in this mess where should we only trust the output of this thing, or as we start like inspecting, maybe not everything is kind of solved, and we are still going to have a job in the next years. Same thing happens when in generative models for images, right? To what extent these generative models are really, in a sense, capturing the entropy of the distribution. It means that it's really capturing all the diversity that is in the distribution, as opposed to just maybe picking up some examples from the training set and just modifying them accordingly. Right? This is a very nice work from the group of Tom Goldstein. So these are basically the generated images with certain prompts, and here are the training images, right? And somehow you can see that the model, in some cases, is just copying what it has seen with a different style. There's one notch further, right, in terms of trying to, how much do we understand these models? Now we are in this world, in this area of what we call prompt engineering, which is something completely impressive, right? So for me, the way I think it is some kind of like optimal control, right? You think about large language model as something that you have some control, that is the, the input to the model, and then you get something on the output, right? So the question is, how can I, modify the input to obtain the desired behavior in the output? This is what engineers have been doing, in many, many systems, right? In mechanical, just understand how to control everything, right? So this is an example. I don't know if you see it or if this is sufficiently large. This is an example of questions that basically just amount to counting how many odd numbers you have in a prompt. So this is wrong thing, but then magically you change the prompt by, giving the model a little bit of help, and now suddenly, boom, it basically goes from the wrong answer to the right answer. Okay? Yeah, fine. Now these things have basically come to a whole new level. I was completely amazed. Now there's even like startups that call like prompt perfect, that elevate your prompts to perfection. So basically this has become really like a like an art. And if I have here some people in the room that are more like engineers, mechanical engineers, to me this reminds me about this problem of, I don't know if you're familiar with this, hearing the shape of a drum, right? You have an object, a complicated thing that you don't know, and you are just throwing signals at the signal and see how the system reacts. And basically this is called the inverse scattering problem, right? So it's a very complicated inverse problem, even for trying to understand, let's say, the shape of a planet or the composition of a planet. Imagine having to do this inverse scattering for a big language model with billions of parameters. Completely crazy, right? More mysteries, right, that I find kind of, this is the time we're living, right? So we have amazing works from different labs. I believe this is work from OpenAI, like Power and Yanni Bourd and others, that they come up with this notion of grokking, which is something that is also a surprise, that you have a certain task, it's kind of algorithmic task, doesn't matter here, and what you see is that suddenly you have a training that looks pretty bad, right? In the sense that the training accuracy is very good, but the validation accuracy is very bad. So any engineer would have stopped, gave up on this thing, but you train a little bit more, and suddenly, boom, the model learns how to solve the task, right? No idea why. Other phenomena is, I don't know if people are familiar, is when you study gradient descent. An important hyperparameter in gradient descent, perhaps the most important hyperparameter in machine learning, is the step size, right? The discretization step of gradient descent. So somehow, what we see here is that there's some kind of very interesting interaction, feedback interaction between how you choose the learning rate and which parts of the landscape your algorithm is going to visit. And sometimes this, having a large learning rate happens to be a good thing, which is, again, anyone who's studying numerical analysis, when you think about gradient descent, you view it as a discretization of something that has better structure, right? Gradient flow. So the smaller the step size should always be better. So here we have these kind of non-monotonic phenomena in deep learning. So how to make sense of all these mysteries, right? Clearly, we cannot hope to, write a paper that says, okay, here's an explanation of everything, right? We need to actually start to, to open this black box and try to identify what are the core properties, whatever the core questions that we really want to focus, right? And this is, the talk today is giving a little bit of my personal perspective of what do I think that are these first order problems, right? Like what are the key properties that we want to try to understand mathematically. So basic questions. So I'm going to start with one slide of statistical learning, machine learning 101. I hope it's just one slide and one equation. So most of the algorithms that do supervised learning, they are based on what we call this empirical risk minimization. This is just a fancy word for doing, minimizing the training error, right? So you have some empirical like the training loss, that is the kind of, you can view it as an empirical estimator of an underlying test error. You have some model that sends parameters to functions, right? And then you optimize the parameters to, to hopefully get as close as you can from this ground truth F, right? F, think of that's kind of the ground truth of the model. And so first thing that you do probably in every course of machine learning is they tell you that, okay, if I understand the performance of a machine learning model, like the performance on the test set, I can view this error as the sum of two errors that are fundamentally different, right? There's one part of the error that comes from what we call the approximation. So here there's no, you can see that there's no data, right? Here is everything is like at the population level, with basically measuring the gap between the training error and the test error, right? This is a standard thing to do. And so what we also learn in many books in statistics is that there's always a trade-off, right? I mean, here the only free parameter for the learner, for the statistician, is to choose this guy, right? To choose what is the function class I want to use. So we know that if we make the model bigger, right? Well, there's of course, as you change the size of the model, there will be like a trade-off between these two sources of error, right? Approximation is in fact like a bias term, and the estimation is really like a variance term, right? You're just looking at the fluctuation between a random variable and its expectation, right? This is a variance. So we know that this is the classical thing that we learned, and now we also discover, like many authors, starting actually from very nice empirical work by Beham, Nishabur, Natis Revo, and then also like Misha Belkin, Daniel, and Sue and others. They really showed us that there's something more to this curve. This is what they call this double descent, right? The test error at some point starts to go up. This is kind of following the standard thing, but then suddenly goes down again, right? And this is what they call this interpolation threshold, or what we call this memorization, right? This is the regime where you have enough parameters to fit the training data perfectly, okay? So natural thing that you would like to understand is how can we find a framework that explains this picture, right, for general models? Another thing that is a basic question for me that I think piqued my interest has to do with generative modeling. Okay, so this is the example that I showed you before. So these are pteros. I believe that these are birds that you guys know. I guess most of us right? So this is actually, I think, the national bird of Uruguay. And so this is these are real pteros, and these are fake pteros, right? That were generated by a fancy model that I just used from this open source thing, Dream Studio. Okay. So I'm not talking about how you train this model. This is a very complicated thing we're going to talk later, but just how do you sample from a model? What does it mean to get a new sample from a probability distribution? Okay, so this is a procedure that in fact we know from first principles that it's a procedure that is actually fundamentally hard to do, especially when you are in high dimensions, right? And this is really a phenomenon that really has roots in physics, right, in statistical physics. And so think, for example, here I've replaced these pteros by just, let's say, the configuration of carbon atoms, right? So they are driven by, there's certain molecular dynamics, there's certain energy, right? That involves like kinetic energy, potential energy, all this stuff. And this defines like an energy surface. And then the probability to find a bunch of carbon atoms in a certain state, you can view it, you can model it with what we call a Gibbs distribution, right? It's something that is exponential to minus the energy. And so in this energy landscape, what you see is that there are some big regions, right? In particular, this is maybe a region where you would want to be, right? Where you have certain configurations that we call metastable, right? In the sense that if you let the carbon stay there forever, right? Eventually, it will go from that state to that state. The problem is that it will take a huge amount of time, right? If I want to sample all the possible ways in which a carbon will be, I want to spend a lot of time. If I'm here, I'm going to spend a lot of time here before I want to switch in that state, right? So this is what we call in physics the metastability. So this is basically, a question is, how can these generative models do, sample from distributions that have this property, right? How is this even possible? Another basic question I have is this basic premise of foundation models, which is the basic premise of foundation models, that is this notion of self-supervised training, right? So the way it works is that you have a big neural network that is trained just to predicting the next word, and this is one phase of pre-training. And then once this thing has been solved, I use the trained model to solve a bunch of other things that might happen later. So this is actually a question that how can we find a framework that explains this procedure, right? The ability that you can actually extract interesting features from a task 1, and then that these features become useful for task 2, right? This is like one aspect that, as we'll see later, it's not shared. It's something very specific to deep learning, in the sense that if you replace this training procedure by, let's say, a kernel method, it would never be able to do that, right, by construction. All right, and the last question is, I guess, a question that I'm listing here, but probably are not going to have time to talk about so much, is the role of the architecture, right? So, as you know, the transformers are everywhere in many of the success stories of machine learning these days. So if you want to understand what is a transformer, you have this diagram. So I don't know you, but I don't have no idea what it is, right? I mean, I view this as a bunch of boxes, arrows, and words. What does it do, right? What is actually, what are the, how can we talk about this model to, let's say, undergrad, right? And, hope that he understands something, right? What is the math behind these things? So as I said, I'm going to spend a little bit of time expanding on the first two things I talk about. So I'm going to basically give you kind of the state of affairs of what do we know in terms of understanding feature learning. And I'm going to, the disclaimer is that it's going to involve neural networks that are maybe not fancy like, transformers, etc., but they are shallow neural networks. But already I'm hoping that I'm going to give you some interesting mathematical ingredients. And then I'm going to talk about a little bit of generative modeling. If you're interested in the third thing of, the advantage in terms of approximation of self-attention, maybe you come to see me offline, because by all means, I'm not going to be able to finish on time. Okay, so I'm going to focus on the first two. And by the way, okay, questions are always at the end, right? Okay, so maybe just leave all the questions at the end. All right, so let's go into this feature learning question. So as I said, it's really like the core component of many, many pipelines in machine learning, right? Where the premise is that we can use an auxiliary task with lots of data to learn interesting features that then we can use much quicker in another task. And as I said, this ability is completely absent in what we call linear models, right? Linear models are, think about kernel methods, right? Where I have some handcrafted features, right? Phi of x that I have obtained through some offline procedure, and then I just fit this linear coefficient, right? If the features are fixed, obviously there's nothing to be gained by transferring from one task to the other. And so, as I said, let's try to understand, why or the conditions in which feature learning emerges in neural networks. And again, disclaimer: I'm going to use shallow here, right? I'm just going to start by something step by step. Okay, so shallow neural networks. So here's a shallow neural network. It's a very simple diagram. So you have some input layer that is like some point in high dimensions. Then this input is sent to some hidden layer that has a width that we can call m. Like there's one parameter that is the width of this hidden layer, and then this is mapped to some output, right? So I'm here really looking at the simplest thing, where I have a function that maps a point in high dimensions to a scalar. And what are these functions? They are linear combinations of simple functions that we call rich functions, right? So think about this little function here that has some parameter theta that parameterizes some maybe like affine transformation of the input composed with some element-wise activation function, like the ReLU or something. Okay? So with this simple function, I cannot do much. But here, what I'm going to do is I'm going to construct a bunch of these simple functions and do linear combinations. Okay? This is the space of shallow neural networks. So what do we know about this model? Actually, this is something that is a model that has a long history, right? So this is something that was studied a lot, even in the 90s, right? From the theory, like the community of approximation theory. So what are the things that we understand? We understand the capacity of this class to approximate continuous functions, right? So if I have here a continuous function f, right? I can maybe construct an approximant that is in that class, right? This kind of a piecewise linear model. And I can understand to what extent the blue curve converges to the red curve, okay? This is really a universal approximation, right? That as I have more and more neurons, the error goes to 0. The other thing that we understand is not only that the error goes to 0, but also at what rate goes to 0, right? So we know that, in fact, why do we need to make the width of the network to make the error 0? And here there's a first surprise. I mean, for the people who are not familiar with this kind of rates, there's something that is a little bit scary here, right? That if you look at the rate, there's a dimension in the denominator, right? And this is what means a curse of dimensionality, right? Is that if I want to make the error twice as small, how many neurons do I need to add? Well, I need to double the number of neurons, okay? Like exponential, there's an exponential dependency. And then there's also an interesting thing that emerges, right, in these works from the 90s, that there's really like a big separation between what we call linear and nonlinear approximation, right? I'm going to just describe very briefly what it is. So what is a linear approximation? This is the simplest one, right? In linear approximation, I view this model as someone is giving me a bunch of parameters theta, right? So the thetas are fixed, and then I'm only going to learn the linear coefficients, right? The output coefficients, basically I'm just going to learn what is the best linear combination of fixed features to approximate the target. In nonlinear approximation, I can move everything, okay? So I can change the position of the neurons and try to make the error as small as possible by combining the two errors. And so the key advantage, as you can see, right, this always has to be smaller than this, right, because I have more degrees of freedom. But then how much do I gain? How can I quantify this advantage? Well, so here you can see the very nice thing happening, right, is that in one case, if I only do linear learning in certain class of functions, I'm still cursed, right? There's no way I can make the error quantitatively small. But in the other case, if I do nonlinear learning, suddenly the curse of dimensionality disappears, right? This is good news, right? So this somehow tells you that there is really an interest in these models to do nonlinear learning, right? This feature learning. Okay? What else do we know later? Okay? Later, we also learned that not only we can understand very well the approximation properties of these models, but there was this nice work by Francis Bach that also shows that we can also control the other source of error, the estimation error. Okay, so basically what it means here is that they look at this particular class of functions, right, that are somehow, that I don't need to explain well, but there's an interesting class of functions where I can control both approximation, and estimation. Okay? And we also know from also these nice works in the community from Ronan Eldan and Ohad Shamir and others, that we can also understand very well how these functions that can be well approximated in shallow neural networks, we can also understand the limits, right? We can understand also how to construct more complicated spaces of functions for which we can really understand the difference between shallow neural networks and deep neural networks, right? In the sense that adding just one more layer can basically make the approximation error go from very bad, exponentially bad, to something that is polynomially small, okay? But the question here is, okay, we understand a little bit the approximation. This happened in the 90s. We understood statistical learning. This happened in the 2010s, if you want. What about the next thing, right? I mean, here everything is about, math, right? But what is the algorithm to learn these functions, right? What about the computational aspects? And this is what turns out to be the complicated part of the question, right? The last piece of the puzzle. And I'm going to describe a little bit what is the framework that we have developed as a community to understand this question, right? What is the algorithmic cost of feature learning? Okay, so this is something that happened much more recently, right? In a series of papers from 2018 and 2019. So here we have again this shallow neural network. And now I'm going to just declare, I'm just going to write things a bit more compact, and I'm going to view every parameter of the neuron, right, as just one point in some Euclidean space, right? Let's collect all the parameters of every neuron in one vector. And now we can see the network as a collection of points, right, in that space. Now what we can do is, change a little bit the perspective, right? And we can just view this function, right, as an integral over some probability measure over the space of parameters, right? So this seems like a trick. I've cheated you, right? So what I'm saying is that I have some description in terms of the position of the parameters, and now I'm just going to introduce a new object that is just putting a Dirac mass on top of each parameter. And I'm just using this measure to just rewrite the function. So what do I gain? Well, now what I gained is that there's a dependency between the function and the measure, right, that is linear, right? Here, the parameter, here, this function is nonlinear, right? So there's a nonlinear dependency between theta and f. But now there's a linear relationship between the measure and f, which means that I can somehow use convexity again, right? If I have now a learning problem, right, that I take this function and minimize some error, now I have introduced a source of convexity, okay? And this convexity has been exploited, can be exploited to obtain guarantees, right? If you do gradient descent or gradient flow in the certain limit, right, when the width of the network goes to infinity, you can actually use this construction, this lifting, to get basically global convergence, right? The guarantees of optimization. And so here, what we see here is that the first mystery that I described, how come when you have a very big neural network, the test error doesn't blow up, right? Why isn't the variance completely dominating the problem? Well, so here we are really using this, we are being this over-parameterized regime in a non-parametric sense, right? We are just basically learning a function over a space of measures, right? And so I don't know if you know who these people are, but this is basically a mapping, right, between very classic thing, right? Statistical mechanics is really based on this going from the, Lagrange to Euler, okay? So everything stays in Europe, but I guess, yeah, from maybe France to Switzerland or something, right? But this is really something that has proven quite successful here. Okay, however, this is not everything, right? The convergence in the width, I told you that these things seem to be going well when the network becomes very wide, right? When there's many neurons. Well, this is still not helping me, right? Because I cannot run with infinite number of neurons. So how is the rate? What is the dependency in the size of the network? Bad news, right? In the general setting that we have described so far, we are, again, cursed by dimension. What does it mean? It means that if I have some distribution over parameters, right? Think that your parameters live in a space of dimension that is similar to the input dimension, right? Your parameters of the network, you have a huge amount of dimension, right? The parameters. So you put some probability distribution over that space. If I want to get good guarantees of the training, I basically need to grid the domain. I need to put one unit of mass basically in every little region of the space. And as you know, this is exponential in dimension, okay? And in fact, we know that we can actually get computational hardness, right? So this is like kind of the TCS part of the slide of my talk, right? Is that if you are interested in proving lower bounds, things that are impossible to learn, well, we can do that for shallow neural networks, right? So there's actually things that we have developed where we can actually find certain neural networks, certain functions that we can very easily approximate with a shallow neural network, but we can prove that you will never be able to learn them with polynomial amount of data, okay? And this is using several techniques. I'm not going to expand on those. So what about positive results? I mean, everything seems here, that I'm, every time hoping that for a solution, and then every time there's something wrong happening. So what about positive results? So positive results, we are, again, this is again something quite recent line of work that me and some of my colleagues in the community we are developing is really to look back again at the concept that I think really was core in applied math many times, like sparsity, right? Sparsity, has been like maybe the success story of statistics and applied math in the last 30 years. So here we have the same thing. Okay, so we are basically we need to forget about trying to get convexity through this measure, right? This is not going to be quantitative. We really need to get our hands dirty and understand non-convex dynamics. Okay, so we can do that under certain assumptions. So these are assumptions where the target function, right, the function that you try to learn, in fact depends secretly on a small number of variables, right? So a function f, I can write it as first I do a projection in a subspace, and then I pass this through some arbitrary nonlinear function. I was trying to find an example to visualize what is this function. I thought maybe this could be a good example, right? So you have a function that, like if you slice it on every plane, right, it looks like the logo of the Batman, but if you view this function along the direction of the rays, this function is constant, okay? So these are the class of functions that we have here, okay? So we make this assumption on the target, and we also make an assumption about the input data. We make an assumption that the input data is invariant to rotations, right? This is I don't know if someone here in the audience can really see why is that, but this seems to is an important key assumption. So in this context, I'm going to tell you basically the punchline, right, of these results is that we can take this target link function and we can define two numbers, okay? So one number is basically looking at what is the degree of the polynomial, the smallest degree of a polynomial where I get non-zero correlation. So this measures somehow, in people here do kind of wavelets, it's what's called a vanishing moment, right? It's like the first non-zero correlation with the target function. And here I'm looking at the opposite. I'm looking at the largest degree in which I have non-zero correlation, okay? So the punchline here is that if I do feature learning with neural networks, I can learn this function using a number of samples that is basically d to the s, where s is the smallest degree. Where if I do like NTK or like learning, using a kernel method, I have to pay d to the r, right? And as you can see, there can even be cases here where this thing is arbitrarily large, right? So obviously you always know that S is much smaller than R, right? So here we have an example where, of course, we have assumptions, right? But we can quantify exactly the benefit of feature learning, right? It's an example that I like. All right, so just as a wrap up on this part, I basically talked to you about a few things. So I talked to you mostly about feature learning, and I kind of argued that this is a key component of neural networks, right? So anything that we want to understand about these like big language models or more complicated things, there's one part that you cannot compromise. That is, why can I learn useful features that then can be transferred somewhere else, right? And so in the context of shallow neural networks, we have some idea on how to start to do it. Okay, is there a mystery on this like overparameterization? I would say not so much. Okay, here what is reflecting from all this work is that one needs to view neural networks really in what we call non-parametric view, right? You have to view a neural net as a function, and even if the neural net has 200 billion parameters, right? You can still assign it a quantity, like a norm, right? That you can still optimize, right? So somehow what drives the generalization of neural networks is not how many parameters they have, but something a little bit more intrinsic, right? And finding this intrinsic quantity, obviously, is not always, we can do it for shallow neural networks, but open question for you guys, how can you do, follow this research program on deeper architectures, okay? There are many questions that remain, right? So for example, we still don't understand basic questions of if you change the algorithm, if you change gradient descent by stochastic gradient descent, or if you do Adam, all the theory kind of breaks, right? So many things that we still don't understand. All right. What about now image generative models? The goal here is, as I said, given a bunch of samples that are, I assume that are IID from an unknown distribution, I want to, the goal of generative model is to find a probability distribution that maybe speaks from some class. And what do I want on this probability distribution? I want it to have good test error, right? So think about this as a very informal way to say that I want my, my probability distribution to agree with the true distribution, measured with some metric, right? I don't want to be specific here, but I also need this object that I have learned to be so I can manipulate it efficiently, right? What I mean is I want to be able to produce samples, right, efficiently. Okay? So here in this example, somehow I need to have like a procedural algorithm that can run in reasonable time that promises me to get true samples from this distribution. Okay, so this problem, of course, generative modeling in deep learning is, a field that has been quite hot and quite popular in the recent years. And here again, I'm framing this question from the same spirit as before. I want to have a framework where I can control all the sources of error at the same time, right? Same thing as we did before, but now there's a new, there's a new guy in the game. There's a new player in the game, which is sampling errors, right? Not only I want to understand optimization, approximation, and estimation as before, but I also want to understand sampling questions. And so there are a bunch of frameworks, right? A bunch of algorithmic, families that people have developed over the last years that somehow, the question is how much do they fare with respect to these kind of four sources of error, right? So I guess all of you here are familiar with GANs. So GANs, one could argue that they are hard to analyze because they are always sitting on an optimization problem that is fundamentally hard, right? So if you think that non-convex optimization is hard, wait until you study non-convex, non-concave optimization, right? It's an order of magnitude harder, and there's basically no hope to get any kind of guarantee. Could this be the reason why these models are maybe not giving good results? Who knows, right? That's an interesting hypothesis, but as a question about trying to find models, foundations, this is an important limitation. There's other models, for example, variational autoencoders, normalizing flows, where basically they have similar shortcomings, right? In the case of, for example, variational inference, one needs to understand it's not easy how to quantify approximation properties, right? There's a lack of consistency, and so I would say, as a model like this, right, one could argue, why not stick with the classic things like MLE? What's the problem with MLE? Maximum likelihood estimation, right? That's what we all learn in undergrad. Okay? What's wrong with that? So let's look at it. Let's write down what is the maximum likelihood estimation for this problem. It's just I have a bunch of data, I have a model, and I need to basically maximize the log likelihood of my model in the data that I have seen. In the framework, in the picture, in the tools that I described, you can view this as an empirical loss of an associated loss function, right? So this is actually the ERM, the empirical risk minimizer, of trying to minimize what's called the Kullback-Leibler divergence between two distributions, right? So the metric that is based on this model is basically the, I don't know if you're familiar, it's a divergence that is called a Kullback-Leibler divergence. Okay, and so if I expand this a little bit and I write down my distributions in Gibbs form or energy-based form, right? I can view my pi star as some, parameterized by some function f star, energy f star, and my model also parameterized by this function f theta, right? So this z minus 1 is what's called the partition function, right? This is what makes the model into a normal in the probability distribution. So I can take this formula here and replace f's in this equation, and I arrive at this optimization problem that has two terms, right? They're very different. And so if you have never seen this thing before, you might say, okay, so what? But if you have seen this before, you can identify here a term that is called the free energy, right? Which is the log of the partition function. And this is really, the reason why statistical mechanics, like statistical physics exists, right? The reason why this thing is complicated to study, there's a whole field, right? And actually, a Nobel Prize last year, Giorgio Parisi, was given the Nobel Prize mostly for his insights in this model, right? In this function for certain models. And so the point here, the punchline is that if I want to be able to use this as a learning framework, okay, I need to understand how to compute this guy efficiently, right? I need to optimize. I need to take gradients with respect to this guy. So this is essentially equivalent to the ability to sample efficiently from my distribution, right? It's essentially the same problem. So the natural question is, when is this possible in high dimensions? And here's another guy from the early 20th century that I guess, I don't know if people here recognize, right? But this is, again, a person who, really set the foundation of this question, right? So this is actually Henri Poincaré, okay? Another French, sorry. Okay, so basically, Henri Poincaré basically said that, in fact, it's essentially the only class, right? So the only situation where I can solve this problem in high dimensions is when the energy, right, the log of the distribution is convex, right? These are the kind of landscapes where I can essentially sample efficiently in high dimensions, okay? And the way you can think about this is that sampling from this distribution is grosso modo equivalent to solving a convex optimization problem, right? We know how to solve convex optimization. But remember, this is an energy landscape. If I view this as a probability distribution, it seems like a bit boring, right? There's basically just a single mode, right? It basically looks like a Gaussian. There's no much I can do. However, if I want to go from this more maybe interesting landscape that has different modes, right? Well, you could say, if I take this analogy, if this was convex optimization, maybe this would be like non-convex optimization, right? Solving this problem would be like non-convex optimization. You would be very wrong, right? Because in optimization, we only care about finding one point that has low energy, right? Just finding one is good. So finding one local minima that is, has good energy, you are solved the problem. In sampling, we need to cover all the modes, right? We need to be, if I want to have a good sampler from this distribution, I need to be able to sample everywhere, okay? And this is really what I call this, there's no escape ticket, right? There's no way I can just rely on non-convex optimization to solve this problem. And the reason why this is the reason behind this is, for those who are familiar, is that there's this notion of functional inequality, right? That somehow the distributions that are log concaves have like a Poincaré constant that is tractable. Anyway, so how to build models? I want to get basically guarantees, so I want to stay in this world, but I want to be able to model interesting stuff, right? How can I combine these two things? And there's a key insight that is just to use Bayes' rule again, okay? So now I can build probability distribution models that I can just write them in factorized form, right, using Bayes' theorem. Okay, I can build a joint distribution that is, contained, that it has like a different, like this vector x, maybe has different parts. and I just write the joint distribution as a product of conditional distributions. But each conditional model, I'm going to ask it to be log concave. Here's an example. Okay, so if here's a distribution that is jointly log concave, right? If I look at the margin, this is actually a log concave distribution. Here's a distribution, that kind of a banana distribution, that is not log concave, but it's marginally log concave, right? So if I just look at the slices along every direction, right, I get things that are basically always log concave, right? Okay, and so this actually inside has been used, is basically at the core of this new family of models that basically are the ones that are powering, DALI and all the things that I showed you before. They're using this kind of framework, right? And so the way these are used in the score-based diffusion is to basically take my input x and lift it, right, and put it in a bigger space, right, such that the point I'm care about is maybe one of the corners, right, is the last point is like x0 in this process, right, and then I build a joint distribution, the whole vector, as basically the solution of what we call a Orsten-Uhlenbeck process, right? If you don't know what is an Orsten-Uhlenbeck process, doesn't matter, right? It's basically some kind of a path, right? You basically go from modeling a distribution over the space of images to modeling a distribution over the space of paths of images, like of movies, if you want, right? And it turns out that in the space of movies, right, we can actually get good Poincaré constants, right? That's the whole idea. And this is also something that, personally, sorry for the personal plug, but this is also something that we are using in the context of more like a physics, right, to model scalar field potentials with basically a much simpler lifting scheme, right, where we just view this vector, random vector here, as the vector of coefficients of orthogonal wavelet decomposition, right? In that case, we can build very efficient, very fast models that actually are good, that are used in what's called scalar field potentials to model certain aspects of phase transitions. All right. Okay. So the takeaways I want to, emphasize here is that to understand generative modeling, again, from a first principles perspective, we again need to be able to understand in our mathematical framework all the sources of error that come into play. And here there's an interesting twist in this problem. That's why I find it so exciting that somehow sampling is a fundamental primitive in this problem that has really like very, very deep roots in physics and actually geometry. And this is actually why I think this score-based diffusion is it's one of these rare examples where a new algorithm that has excellent, like the very impressive empirical results, also has very appealing theoretical properties, right? So somehow I would think that this is the right path to go forward. We still don't know many things about it. So for example, we cannot characterize what are the target distributions for which this framework, this algorithm, is going to give you an advantage over another algorithm, right? I was mentioning about GAN, so I was mentioning about VAEs. So one thing that you would like to understand is, can I have some kind of theorem or some kind of results that quantify, in fact, you should be better using this method than this other method, right? This we don't know. Another thing that is, I think, fascinating and interesting is explore the connections between, so as I told you before, this score-based diffusion model, they basically operate by lifting. Trying to model, instead of modeling the distribution over images, you go into distribution over paths. And this is naturally something that becomes like a coupling between two distributions, right? And there's a fundamental framework, I guess Marco might tell us a little bit about this afternoon, on how to address this with optimal transport, right? Which is really interested in this question of how best to couple two probability distributions. All right, so actually, how am I doing time? Pretty good? 5 minutes, yeah. But I want to leave some minutes for time for questions, if you want. Yeah, okay, so I have I'm going to be done in 2 minutes, if that's okay, and then we have more questions. All right, so just as a concluding remarks, actually I've been a little bit faster than I thought, but okay, so just also from the perspective of someone like me, who is mostly interested in theory, right? There's always this feeling as a theorist that what is the point, right? Because you finish, you are very happy getting this result for shallow neural networks, and then suddenly people are going to use, a completely magic architecture on a problem that has nothing to do with regression, right? So there's always this sense that we are always far from the edge of applications, and even the gap is growing, right? So, I don't know if a certain derivative, right, of the thing is actually changing an inflection point, but I think that nonetheless there's progress, right? We are able to understand more things, right? And as long as there's progress, I'm happy. Doesn't matter if the things are doing much better. One of the things that, for example, things that I didn't talk about, that I also think that as a theorist or even as a community, I think we should be maybe trying to dig deeper a little bit. So one thing that, for example, I would be happy to understand better is this theory for neural scaling laws. So scaling laws, as you know, is this empirical observation done in these big labs like OpenAI and DeepMind, where there's basically you can actually just do like you can fit a very simple like a 1 or 2 parameter model on how does the performance of the model depend on the amount of training points I have, the amount of parameters I have, and how much training time I have, right? And if you do these regressions, you can realize that you should make everything bigger, right? Because the data seems to show that they can always go into the direction of improving. What is the theory for that? Can we actually build models? So if you remember what I said in the shallow model, right? We have some results that kind of link the number of samples, right, with the dimension of the input, right? Like D to the S, right, was this thing. So this is what we call a regime that is, I don't know, to what extent it's relating to this scaling laws. The other thing that I'm also interested is this new question of in-context learning. I don't know if the person talking NLP will describe it, but it's this kind of new word that somehow these language models, they are, there's some stuff that they learn in the parameters, but there's some stuff that they kind of extract from the context, right? Is there something here, or is it just like renaming, like the classical when I have learned a probability distribution, I can always condition it, right? I can take some context and just ask for, like do inference by doing a, sampling from the posterior distribution. So is this, or is it something more? That's another thing I would be interested. So with that, I will leave you with this poem that somehow links a little bit some of the things I said. And this poem is not written by me. I wish it was written by me, but this is written by ChatGPT. So I live with that, and thank you very much.
Hello. All right, thank you, Joan, for the amazing talk. Questions? There's one question over here. I'll bring it.
Hi, thank you very much. It was a great talk. In the part about representation of features and learning that, there was a theorem that you mentioned on separating sort of kernel machines versus
yes.
wide neural networks. It seems like what you were trying to learn was sort of a wide neural network, and of course then you would need a lot of samples to do this with a kernel machine. Is there an analog the other way around where you have something that is very easily expressible by a kernel machine and you can learn then with a kernel machine versus a neural network?
Good. Good question. So you are right that if I have some target function that I can kind of design to have a small norm in a kernel space, and I try to learn it with feature learning, I'm going to pay a little bit of extra cost, just because there's an inclusion, right? That like everything that is in one space is in the other, but somehow you would be statistically optimal to put exactly the prior. If someone has promised you that the function that you're looking for is in this like RKHS, has some like a RKHS ball, then you should be using this as a prior. So in that sense, yeah, there's kind of academic examples that you can build. But I think there's another side of your question that I think it's much less clear, which is, what about in practice, right? So in practice, how much should we be relying on the feature learning versus how much at which point we can transition, right? From maybe we can do like a few steps of feature learning, and then once, maybe there's a point in which we can just stop the complicated algorithm and just do like fit this with the kernel, right? Just like the features are good enough, and then we fit. So this is a question that is, in fact, some of the work that I cited here. So this work by Alex Damian and Jason Lee and Mahdi, and this work by Jimmy Va and others, they do precisely that, right? So they say, okay, I'm gonna just do, actually they do one step of gradient descent with the features, and then with one gradient step, I'm gonna just fit a kernel and see whether the kernel I've learned in one step is quantitatively better than the kernel I started with. So they basically explore this idea. Yeah.
All right. Questions there? Ah.
First of all, thank you and congratulations. Was a great presentation. More than a question, this is like any kind of curiosity, maybe. Before I come here to Montevideo, I was talking with some friends, students of the University of Havana, about what's more important, model performance or model accuracy. We observed that the majority of people justify the need of both performance and accuracy. And of course, both of them are very important. But specifically in a deep learning model or a DL algorithm, what do you think is more important?
Okay. So the question is comparing model performance with model accuracy? Yeah. Okay. I guess that you might be thinking in terms of accuracy as a classification problem, and then performance as some like cross entropy. So if I understood your question correctly, you have maybe one loss that is used, like what you call a surrogate loss, that is used for training the parameters. And then you have another criteria for measuring how good is a network, maybe the classification error, right? And sometimes these two quantities might have a gap. And this is, in fact, what is behind perhaps this. Let me just go back, sorry. Here, right? So this might be, perhaps one of the things that that are in the back of your question, that, we are measuring accuracy of a network, and we have the impression that there's nothing changing with the accuracy, but maybe there's some kind of inner state of the system, like some kind of other function, other cost function, that is secretly, slowly getting better, right? Except that we cannot measure it. Maybe there's, in these experiments, we don't know what it is. So in that sense, I think that this question is a complicated question, right? So even for convex models, right, there's still like a, very limited understanding of in what conditions optimizing function 1 is going to give you better performance in function 2, right? But obviously, in these kind of tasks, we are forced to use a surrogate just because classification error is not differentiable, right? So if anytime any kind of a, gradient-based learning needs to somehow consider like a surrogate function. So yeah, this is things that I don't know. I don't have much insights, unfortunately.
All right. Some other question?
Hello. Great presentation. I have a question regarding the issue with lifting the problem of sampling from a probability distribution to sampling over paths. Because I cannot see very clearly how this could affect metastability, in the sense that if you have a local minimum in the probability space of your probability distribution, then you are also going to have the same issue in path space, right? When you do displacement interpolation or something like that. It's
a good question. So think about, you have a landscape that can have like a lot of valleys, a lot of things. And now what I'm going to do is I'm going to consider like an homotopy path. So let's say that you are blurring the landscape, right? So somehow what you're doing in essence is constructing a saddle point, right? Basically, you can always connect like the paths, right? at the beginning, at time 0, they are going to be, as you say, completely exposed to metastability. But paths somehow start to get closer to each other at large times. So somehow think about like large times as giving you, like introducing you like a saddle point. So you can always go through you can always connect any point with any point by first, increasing t a lot. In that world, everything is, there's no metastability, and then you can go back again, right? And so, yeah, this is actually a fundamentally good insight, right? And this is, I think, it's not the detail, right? And this is, also beautiful. There's a lot of beautiful math that is behind this.
And this is very different from sampling paths from the sampling distribution.
Exactly. Yes.
Hi. Great talk. Thank you for that. I wanted to ask you about the on this topic permutations for studying these basins of attraction. There's been some works on that for knowing if different networks
yes.
work the same, if there's a permutation acting over the weights or the
yes.
or the activations.
Yes.
So I wanted to know if it's somehow connected.
That's a good question. It's a good. I didn't think about this. So you would be thinking, okay.
There's been a recent work. I think it's Git rebasing or something like that.
Yeah.
There's been like such.
Right. So the question would be, can you use some kind of homotopy path like this to find a better connection between different networks, between different basins of the neural
because it wasn't. The idea will be to close the gap. And some
it's a good idea. I think it should be. We can try to develop it. It's an interesting insight. Yes.
Okay.
Yeah.
Thank you.
All right. So let's thank Joanna again for the great talk.
And we will move now to the spotlight speakers. So Diego Galeano, I don't know where he is. There, great. And then we will have Anna Magidman here. Okay, great. Both. Hola, ¿cómo va? Desde acá.
Ahí. Ahí es mejor. Okay. ¿Y esto?
Bueno, okay. So, great. So our next speaker is Diego Galeano. Diego is a researcher in AI at the Faculty of Engineering at the Universidad Nacional de Asunción in Paraguay. He received his PhD in computer sciences from Royal Holloway, University of London. During his PhD, he also worked as a research fellow at Yale University and at Imperial College London. He also worked as a postdoctoral researcher in data science at Fundación Getúlio Vargas in Brazil. And his main area of research consists of applications of AI in drug discovery and medicine. Thanks, Diego.
Thank you, Enzo. Thank you so much for the invitation. It's great to be here. Sharing a little bit of the application of ML. I know everyone here is more like theoretic, it seems to me, working in the theory area of ML. How can I use this? Okay, fantastic. So as Enzo said, I work at the National University in the Faculty of Engineering as well. And I'll be talking briefly about some of the research projects I work on and also some of the other research groups that are at uni. So in case you want to contact them or understand a little bit better about what they do. I just skipped this slide because I already know. So I wanted to start explaining a bit about the drug discovery process. So I'm pretty sure that everyone here has taken a medicine before, but perhaps you don't know how the medicine reaches to the market or how it is developed. This is usually a process that takes around 12 to 15 years. As you can see there are like different stages of development. Oh, sorry, I don't know what happened. Just looking for the pointer. Okay, thank you. So as you see, there are different stages. This starts with the target identification usually, and it ends with the approval of the drug. Usually, for example, in the US, you have the FDA, but of course, this changes also in different countries. And we are talking about an investment of $1 to $2 billion to have a medicine from the starting point of the research to reaching clinical, to reaching approval to real patients. This is another figure that I like to show because here you can see that the way you start this process is once you have the target, basically, it's called drug discovery because we don't have a rational process to discover the drug. You just hit with everything you have in your chemical libraries. You have 2 million compounds and you just hit the target. Can we find the right target? And this is usually, you start filtering basically the compounds until you find the right one. I don't know if you know this, but usually only out of 10 drugs reaches the market. One of 10 drugs that reach the approval to the FDA will reach the market. So this industry is one of the industry with the highest failure rate. So there is 90% that you fail when you are reaching the last stage of development. And you have spent probably almost $2 billion. So this is, so I'll talk briefly about some of the projects I work on drug safety. So when I talk about drug safety, I usually refer to unexpected drug side effects. I don't know if you've seen these news. These are a little bit old, but there has been some medicines that reached the market. The patients were taking them, and then what happened is that they caused unexpected side effects that we couldn't predict or prevent during clinical trials, and they had to be pulled out from the market, causing huge loss. And this actually have like very nasty implications also for the pharma industry. And also for patients, right? Because the patients were having like heart disease because of the drug, right? So one of the projects that we recently published in self-report methods was we were trying to predict the presence or absence of drug side effects from the data we had in clinical trials. Because the question here was, if we are in clinical trials, can we help the researchers that are working on that stage using some ML modeling to predict the side effects that the drug will cause afterwards? So therefore, on this little figure you can see here, we have some data from clinical trials for the drug that is under study. We annotate some of the side effects, but a lot of them remain unknown. And what we did is we integrated a lot of other information from other drugs that are on the market together with other features. So we know some information about the drugs, like the chemical structure, We have some protein targets, the taxonomies, information, and indications. So I won't go into all this detail on the data because I don't have time, but I will probably expand on this talk on Friday, so if you want to participate, you remain until Friday, I will expand on this. Another question that we asked, this was also a joint work with Professor Mark Stench and Todd Lee. We asked, can we also predict the frequency of the side effects? Because the previous problem was a binary problem. So it's just, we predict whether the drug will cause or not the side effect. But in this project, what we did is actually we tried to predict the frequency in the population. Because you can have a side effect that can happen in 1 out of 10,000 in the population, or it can happen in 1 in 10. So this is called very rare or very frequent side effects. And actually there is a whole scale to define this. And we developed a new metric factorization algorithm to predict this, and you can actually find more details in the paper. Just briefly, I will go into some other projects about drug repurposing. If you don't know what drug repurposing is, it's basically taking a drug that is already on the market for a different use case. So for example, a drug that is taken for some heart disease, we want to use it for cancer. So that would be the concept of drug repurposing. That's why I really like this figure, because you have these old drugs that are already in the pharmacy, and you want to take them for a new disease. And I think this concept of drug repurposing became really important during the pandemic because we had this new disease that we didn't understand, and the question was, like, millions of people were at risk worldwide, and we wanted to know, can we use some of the drugs that are already in the market? We know they are kind of safe for humans. We have a lot of data for them. We can deploy them, like develop them very quickly at deploying at large scale. So to try to help the scientists that were working on drug repurposing projects around the world, we collaborated with this COVID consortia. These 200 institutions worldwide joined during the pandemic basically for this research work. And what we did is we developed 2 different approaches. One of the approaches was based on this drug virus association data that we found together with the stage of development and the model. Basically what we did is we developed this metric factorization model that models the probability of success of the drug for the virus. And then you generate a ranking for the virus in which you are interested in. In this case, it's SARS-CoV-2. The second approach was more based on network medicine. I don't know if you are familiar with this concept. This idea. Basically, the idea is to model the cell as a network of interaction between proteins. And what happened now is that the drug will affect some of the proteins in this network, which is the human cell. And then the virus will also affect some of the proteins here. And then can we have measure of distance between the targets of this drug and the targets of the virus in a way that will tell us about the efficacy of the drug against the virus. Because if the targets of the drug were kind of close by to the proteins that the virus use, then that will tell us whether it is likely that the drug will disrupt the activity of the virus in the cell. So we developed this framework of using graph kernels also to produce another ranking. And what we show in this work is that our results of the drugs that we predicted for COVID align with other experiments that were carried out independently by different research labs at the time. So this was really an amazing project. A current ongoing work, I am also collaborating with Afshin Beheshti from NASA and with Tyson, Robert, and Francisco on this project of trying to develop an ML model for microRNA targets. And if you don't know what a microRNA is, don't worry about it. It's just a small molecule that we have inside the cell that controls a lot of things. So they are master regulators in the cell. So Afshin discovered that there was a microRNA called 2392 that was associated with COVID. So in the samples of COVID patients, this microRNA was dysregulated. So the question is, can we get this microRNA back to normal by targeting the microRNA with the small molecules? That was the idea. And so basically, we ran some ML modeling on some small molecule data that we had, which was really small and sparse, so this is a very challenging problem. But the results were good and interesting, and this was published also recently in Cell Reports. Other research group, Fiona and other work that is being done there. I will just talk about some of the groups that have some AI component in the research, not all the labs because there are too many. So Professor Jorge Molinas is leading this AI for particle physics group, where they are collaborating with Fermilab and the Dune experiment to try to detect muons from some imaging signal that they get. So this is an example just of the classification that they need to do from the imaging. For example, if this is a muon for sure, or this just they are unsure, or it's a spot, or it's a bad pixel. Then there is also the lab of Diego Stalder. He has this lab where he's developing wearable devices, and he uses also some machine learning for developing the devices, because what he discovered is that you can use ML to actually reduce the dimensionality of the data, and this is, can be efficient for these small devices, right? Otherwise, you need very huge medical equipment which are not wearable, right? That is the equivalent of this. And then he also collaborates with other group on some epidemiological modeling in Paraguay. This was a shared work with Paraguay and data from Peru. I don't know if you know, but in South America, usually we had the dengue fever, the chikungunya fever, so we are not very unfamiliar with epidemics, let's say. Although COVID was a really bad one, just for the record, right? And then also there is the distributed system lab run by Professor Derlis Gregor. There is the contact. He has like too many projects to mention everything, but just like very broadly, the lines that he worked on are intelligent transportation systems, precision agriculture, and autonomous surface vehicle. Thank you so much.
Thank you very much, Diego. So is there any question? No? Well, Diego didn't get to talk a lot about the projects. Oh, there.
Oh, sorry.
Yeah, go ahead.
I think I have two, but at least one. But maybe I didn't got from the first project you were talking about, the prediction of side effects in drugs. I was wondering if you were considering the drug chemistry itself features, or just like, you know, with the Monday newspaper, you know, when the people just already took the medicine, and how are you collecting that data? Is there any way of considering the, for example, the chemistry of those drugs and trying to cluster those compounds in the future to predict a new one coming to the market, instead of predicting after the people or the drug is already in the market? Do you get it?
Yeah. So, so that's exactly what we did. So here we frame the question that having data for the drugs only from clinical trials, can we predict the side effects that were detected after all these drugs entered the market? Actually, we did a lot of simulations here to simulate this scenario, and we showed that this problem is really difficult, because sometimes what happens in this community as well of drug side effect prediction is that people tend to do just cross-validation to show you an AU log of 90%, this problem is kind of solved, 95%, but really the reality is that we are far from solving the drug side effect problem, right? So, and these people in the field can tell you this, right? So Regarding the features that we use, you can see them here. Probably I didn't have time to go through this, but we did use the chemical structure of the drugs for this analysis, and this was integrated into the model through a graph representation learning framework, where, so we have, I didn't explain this model, it's called geometric cell expression model, but it's a high rank matrix completion model that allows you to integrate other type of information. Actually, we have multiple sources, and this is integrated into the model as a graph regularization framework using the Dirichlet norm. Yeah.
Okay. Is there any other question? Otherwise, we move in the interest of time. So Diego will be presenting more technical details of his work on the healthcare session on Friday morning. So if you are interested in that, you can go there. Thank you very much, Diego.
Thank you.
Okay, and our last speaker for the session before lunch. Here we are.
Hola, hola. ¿Me escuchan? Hello.
Okay, so our last speaker is Ana Magidman. Ana is a researcher at CONICET and professor at Universidad Nacional del Sur in Bahía Blanca, Argentina. She obtained a master's degree in computer sciences from Universidad Nacional del Sur and a PhD in computer science from Indiana University. She has been a visiting researcher at Washington University and Stanford University, and she currently leads the Knowledge Management and Information Retrieval Research Group at the ISIC Institute in Bahía Blanca. So thank you very much, Ana.
Thank you, Enzo. First of all, I want to thank the Khipu team for organizing such a wonderful event. I'm delighted to be here. As Enzo mentioned, I am a professor at the Computer Science and Engineering Department at Universidad Nacional del Sur in Bahía Blanca, Argentina. And I am also a member of the Institute for Computer Science and Engineering, also at Universidad Nacional del Sur, and I lead the Knowledge Management and Information Retrieval Research Group. I was invited here to give a talk presenting the research lines of our institute and of my research group. So let me start by telling you where I come from. Bahía Blanca is a city about 500 miles to the south of Montevideo. Bahía Blanca means white bay, but well, even if you maybe are thinking of a beach with white sands, that's not the reason why it's called white bay. White bay is just because we have a lot of salt in our shores, so it's like a salty area. And it's not because it's snowing all the time or because we have nice beaches, but just because we have a lot of salt there. Well, let me tell you a little bit about ISIC, the institute where I come from. This is a double dependency institute. That is part of CONICET, our National Research Council, and Universidad Nacional del Sur. The institute brings together more than 30 researchers, 7 support professionals, and about 20 doctoral and postdoctoral fellows. There are several research areas in the institute. Here you have a summary of the main ones, like scientific computing and bioinformatics, software engineering and information system, artificial intelligence, distributed systems, visualization and graphic computing. In particular, there are 5 groups that are doing research in the area of artificial intelligence. Most of them are quite theoretical, probably except for the one in the middle, which is the group to which I belong, and is working mainly on the area of machine learning and natural language processing. But the name knowledge management and information retrieval is due to the fact that during the very beginning, we were working in a project we were participating in a project that has as a purpose to help experts from NASA to organize their knowledge. This was a project funded by the NASA Intelligence System program, and some of the early members of our group were participating in this project. It was led by David Leake from Indiana University and Alberto Cañas from HMC. And during this project, we were applying some sort of traditional text mining and machine learning tools to help experts to organize their knowledge. What we were doing was we were monitoring the experts as they were building these concept maps, and we were suggesting topics or propositions, or concepts, and other kind of resources so that he can or she can extend that knowledge model under construction. Later, we took the experience that we got in this project for context-based search and applied to many other domains. So our group continued working on the area of context-based research, and we were mostly focused on learning incrementally how to refine queries that were able to reflect a rich context. So our goal was mainly to incrementally learn how to formulate good queries automatically from a context in order to accomplish any task that was associated to any domain, right? A more recent project is a collaboration with several members of the group, but in particular with Elsa Esteves, who is an expert in electronic government, and Carlos Chañevar, who is an expert in argumentation system. The project is intended to combine argumentation technologies and context-based search to deliver information in e-government infrastructures. We have edited a book related to this project that can be downloaded for free. And let me briefly tell you what this project is about. Some of the problems that we are trying to deal with is trying to monitor how the citizens and the government interact. So as soon as some ministries make some announcement, we monitor how the citizens are reacting to those announcements by measuring different aspects. For instance, we look at how many times they retweet or how other resources are shared. But in particular, we try to look at the emotions associated with the posts that the citizens present on Twitter, for example, associated with those announcements. So, for instance, we are using Plutchik of emotions to get an idea of how the citizens react. So we can tell the dynamic of these emotions as time goes by. Another related project in the same area is the development of tools to be able to organize the arguments that people have against or in favor of a specific issue. In that sense, what we are doing is we are training classifiers to detect the stance of a tweet, for example, and to organize them in a collective way so that we can get a good idea of the arguments that are against or in favor a specific issue. For example, here you can get a picture of some polarized topic, which is the COVID vaccination. Those triangles that are yellow are those that are very polarized, and then you can have arguments against and arguments in favor. So the interesting thing about this is that you can get a good idea of the collective position of a group of people, but also in our project, like every opinion counts. So we go into very specific opinions, and we try to put each opinion in some way into this dialectic process. Another interesting project that we are currently working in is learning causal models from digital media. This project is particularly challenging because we have to try to extract from massive number of news what we call ongoing events. Ongoing events are different from the traditional events because what we want to do is we want to build a time series, and it is very important for the events that are reflected in those time series to be ongoing, so that, for example, if we find the world crisis, it's not any crisis that we're interested in, but we want to identify an announcement of a crisis that is underway. Probably the most challenging aspect of this project is to build these embeddings of events that then are used to build this time series that are useful for building these causal models. And we have been applying these ideas to different domains like economics, energy demand, and many others. So this is a very general project. Another collaboration that is going underway right now is with Canada, Dalhousie University and St. Mary's University. We are building tools that rely on scalable continuous active learning to help social scientists to deal with large amounts of text. So in this way, what we are trying to do is to provide suggestions on which are the most relevant articles in a lot of newspapers related to some research questions. Another very recent project is one that is going to be funded by STIC AMSUD. Actually, we got the news very recently. This is a collaboration between Chile, France, and Argentina. The coordinators are Jocelyn Dunstan, who will be arriving to Montevideo in a couple of days to participate in Khipu, and Ais Baudot. And what we are trying to, and myself, right? And what we are trying to do is to combine text mining techniques, machine learning, and complex network analysis to build a series of complex networks that are going to be combined in a multi-layer network framework in order to model the way that different patients interact. So we are analyzing clinical data to build those structured networks from unstructured text, right? And well, I'm about to finish now, so this is just a very short overview of what we are also doing in terms of technology transfer actions. Our group is collaborating with CCG in the digital transformation of Banco de la Nación Argentina. Another interesting project is another technological transfer action for Intal, which is a division of the Inter-American Development Bank. And the goal in this case is to monitor Twitter to identify announcements of foreign direct investment. This is a very interesting and challenging problem, not only because we are trying to retrieve relevant tweets and classify them, but also because we have to have a customized name entity recognition that is able to identify the different entities that are interested for this kind of project, like organization, like the origin from the organization from which the money comes from, the organizations to which the money is going to, and many other entities like the amount of money that is being invested and so forth. And also another important aspect of this project is the fact that we want to infer from Twitter information that is implicit, and also we want to disambiguate, and we want to eliminate duplicates. So we have to deal with some semantic information source, and we are using Wikidata for that. And finally, there is another transfer action underway right now for global news, in which we are monitoring also news media in order to detect events and create histories based on those events to organize a large amount of digital news media that this company is already allowing us to use for their project. So this is also a very challenging project that is being part of the several transfer actions that our institute is doing right now. This is all I wanted to tell you. If you have questions, I will be happy to answer them now. Tomorrow I will also be presenting a poster, so we can talk there or any time during the week. Thanks a lot for your attention.
Thank you very much, Anna. Is there any question? One question, maximum. Okay. There is a microphone there, but okay. One where? There. Oh, in the middle. Yeah, you can pass it. Yeah.
Okay, actually I have two questions, but maybe we can stick to one. And how do you detect polarized tweets, the ones in yellow? And more important than that, how would you have liked to detect them? So I guess you do something, but you had many ideas that you could not get to implement. And I guess this is something that interests a lot of people here or elsewhere, and I would really like for you to share your insights with us so that we can keep all working on them. So to steal your ideas, basically.
Right. Actually, what we're trying to detect are polarized topics. So some tweets are going to be pro-vaccine, for example. Other tweets are going to be anti-vaccine. So it is interesting for us to detect those topics, but sometimes we just decide we are going to deal with this topic, for example, abortion or feminism, guns. There are a lot of polarized topics that we already know beforehand. In that sense, the difficult or the challenging part of the project is to detect when a tweet is talking against or in favor. The other problem, that is detecting whether a topic is polarized, is very challenging. And in that case, we didn't make much progress yet. And we are trying to do something like based on opinion mining, and which is not working very well right now for our specific project, because actually the problem of stance detection is quite different from the problem of sentiment analysis. So you can be against something and use bad words, but you can be in favor of something, and you can also use words that are negative in the sense of sentiment analysis. So it's one of the main challenges for us. This is still an open problem for us, but what we are have done some progress so far is on the issue of taking a specific topic and looking for tweets that are in favor or against to build those stance trees. This has been quite successful so far. Thank you for the question.
Okay, so we thank again Anna. Thank you very much, Anna.
Thank you.
Okay, we are now finishing the morning session. The afternoon session will start at 2 p.m. here again. And now you have lunch, you have your tickets, remember? Yeah, and see you here at 2 p.m. Yes. ¿El formulario de qué? Please, one last thing. Fill in the form that was sent to you for the Solis event and what? And the Women in AI event, both forms. And the posters will be happening at from 1 p.m. to 2 p.m. here in the main session.
Hello, hello. Welcome back. It's time to kick off the afternoon session. So we'll start with the computer vision keynote. It's an honor and a pleasure to introduce our next speaker, Jorge Sanchez. Jorge Sanchez is the head of applied AI research at Mercado Libre in Argentina. And he holds a PhD from Universidad Nacional de Córdoba. And also he is the recipient of the prestigious Condering Prize in Computer Vision. So, Jorge, all yours.
Thank you. Do you hear me okay? Hello? Maybe hi, to put it well. Okay, thank you very much for the introduction. And it's a pleasure to be here. I attended the 2019 Khipu, and it's really nice to see how this community has grown over the years, especially during the pandemics, and it's really an honor to be here today. So my talk will be about today's building blocks on visual perception. And concretely, the goal of the talk will be to compare and to reflect on two of the most prevalent computational blocks that drive most of the computer vision models we use today, which are convolutions and multi-head attentions. And the title of the talk tries to reflect, on one side, the speed at which we see advances in the computer vision community, or machine learning, or artificial intelligence in general, and at the same time, to acknowledge some of their building blocks, some models and computational units that are the foundations upon which those developments are possible. So when we think on visual perception, we can start making the exercise of asking ourselves of how vision perception works in our case, and by which mechanisms we are able to transform light into visual abstractions, and more importantly, how can we emulate this process with computers. I stress here the word emulate because at least the goal of the talk will be to see models that try to emulate this behavior and not to replicate it. We are not trying to replicate the human visual system. So one thing we could do here is first ask what we already know and what has been tried in the past, because this will lead us to the computational models we use nowadays. Now, perhaps one of the most influential works on visual perception was the cat experiment by Hubel and Wiesel. I'm sure many of you have already seen this picture. What Hubel and Wiesel found was that the visual cortex of animals had, there are cells, there are neurons, that are specialized to very specific stimuli, to a very specific pattern within the visual field. And for instance, lines at different position or edges at different orientations. And they also found there are other cells that responds to more complex or more general patterns, and that this complexity arises from the composition of more simpler responses. So there is this idea of compositionality of visual representations. The Hubel and Wiesel experiment was one of the most influential works also for the development of the computational theory of visual perception by David Marr. What he proposed was that the visual system work in stages that build upon each other in a hierarchical manner. And the Marr's theory provided us with a framework in which we can build upon and think on ways in which we can emulate the complex computations involved in visual perception. These ideas of, on one side, locality, compositionality, and hierarchical processing were the base that led to models like the neocognitron from Fukushima, or the third generations of convolutional neural networks that were proposed in the 80s. What these models have in common is that at early stages, there are cells specialized on very local patterns, on very specific patterns, similar to the simple cells that Hubel and Wiesel discovered in the primary cortex of the cat. And then you go up to the higher cells, higher levels of the architecture, and by means of composition in a hierarchical manner, with higher layers taking as input those of the responses that were generated in previous layers to compose more complex representation. And this repeats in stages until we reach a representation that satisfies our needs for a particular task. Now, for a computational point of view, at this point, we can transform this sentence that was in the first few slides, to make sense of the visual work into another sentence that this was more operational, which is extract useful information from images autonomously. And by useful, I mean we should be able to deal with different abstraction levels, from lower level primitives like geometry, groupings, and motion and simple motion patterns, to more higher level concepts and abstraction degrees. We can think of this in this case as that we are developing a variable bandwidth channel for visual information, in which at each point we should have access to different degrees of abstraction. And so we can compare it for a variable compression rate of visual information, from the more raw level to the more abstract level, and when we talk about objects and visual concept in general. And for what we know that this should be, or could be, a hierarchical process. And as we will see later, this hierarchical process can be combined with contextual information. And when we say that this process has to be autonomous, I mean that at a very basic level, the agent should be responsible of the understanding part of the process. In the sense that we don't want to hard code or to tell the agent what it should look at, but we should design agents that can learn these patterns from data. In the rest of the talk, a good exercise is to think of this hypothetical agent as a passive agent. I won't talk about the whys of visual perception, like goal-oriented perception or interaction with environment, or even communication with other agents. What we talk about will be about visual perception for the point of view of an agent that observes the world and doesn't interact with it. But then I guess we can build more complex behaviors. Okay. Now that we have some historical context on the on how we arrive here. Let's take a look to what happened to a very biased choice, by the way. This is my choice of milestones. It doesn't have to be yours. But a very biased choice to what happened in the last 10 years in visual processing, and also include some milestones on that happened in the natural language community, because we got a lot of inspiration from them in the last few years. So one of perhaps the first one is marked here, is the introduction of the AlexNet architecture in 2012, where they show that convolutional neural networks were highly competitive, even at large scales problems. Then 2013, Seiler and Fergus introduced the CFNet, which is a refinement of the AlexNet, but more importantly, they show that we could take a model and train it in a larger dataset and in a pre-training strategy, and then fine-tune it or adapt it to a similar problem in a different dataset. And that became ubiquitous in computer vision, this idea of taking a model and fine-tuning or adapting it to a different task. Then we have some new architectures that incorporated these locality details that I talk about the locality of visual processing, the visual cortex, even further by reducing something that will be in the next few slides, which are the kernel sizes. And at the same time, around the same year, in the natural language processing community, Mikolov introduced the word-to-vec embedding that shows that we can use context of the word as signal for supervision, and in this way we can train very, very successful models in a lot of data without the need of strong supervision, and that was really, really important. And during 2014, there were different approaches to model attention, and then in the computer vision community, 2015, Kai-Ming He introduced the ResNet, and that allowed to train larger and larger models because we found a way to deal with the vanishing problems when doing backpropagation. This was also incorporated in the different fields, not only in vision, but also language and other machine learning related fields. Then, in the language community, we come to 2017 with the introduction of the transformer architecture as we know it today by Varswani. 2018, the development of BERT and the pre-training, and this pre-training strategy of pre-training a big model and then fine-tune it for other related tasks became ubiquitous in natural language also. And then fast forward, we arrived to 2020s with the introduction or the adaptation of the transformer model into the computer vision community with the introduction of the VIT by Dorsovitsky. VIT stands for Vision Transformer. And, well, we are here. So if we want to take a look on how important was the introduction of the VIT into the computer vision community, we can take a look to what happened around 2020 and 21. There is a bunch of work around transformers in computer vision now, and there's many more to come. So, what we can say, or we can see, is that in the last 10 years, there are two predominant models in the computer vision community, which are convolutional neural networks and vision transformers. And for convolutional neural networks, there are a rich history of literature on visual perception that back up their main ideas or design criteria. like hierarchical organization, locality, and compositionality. And the main building block of convolution and neural networks is convolution, the convolution operation. And for transformer, they are models that excel at sequence modeling tasks. They are very, very successful. They are very flexible into modeling interactions within a sequence. And a key aspect here is the role of attention and the role of context, because as we'll see in a few minutes, what we do is to model a word or a visual element, in the case of computer vision, that is related to their neighborhood elements. And the main building block here is the multi-head self-attention. So the rest of the talk will be to see how convolutions and multi-head attentions work, and then we will compare them and put it into perspective to see what kind of visual information they learn. Okay, before going to details, some preliminary concept first. We'll assume images are, we'll see images as 2D array, but we'll see them as a stack of multiple channels, a stack of multiple single image channels. Yeah. Images will have a spatial dimension, certain height, certain width, and a number of channels. For instance, if we have a grayscale image, that will be a single channel. If we have a color image, we might have RGB channels. But we can have multispectral images, like satellite images, where you have many, many, many channels. And even you can have a multitude of channels just by designing them to represent different things. We'll assume that if we index such array by a triple, we'll have a scalar value, which first, second, and third entries of this tuple will be row, columns, and channel index. And what we also assume is that we can index this array by a tuple, ij, and by doing this, we have access to a vector, which is the value of the channels for that location, for that spatial location. Sometimes I will tell a 2D array to refer to this spatial arrangement of vectors along the channels. So, and in what follows, we also think of convolutions and multi-head attention as a mapping mechanism that preserve spatial dimensions. That means that if we take an input array, we'll feed these models, these modules, and we'll get another 2D array, or 3D array, sorry. But those arrays have the same spatial dimensions. The only difference is that the number of channels might differ. It might be larger, it might be smaller, or might be equal, but there is no constraint there. Okay. Let's see very briefly how convolution works in this case. And let's first start with a simple example with an input image that consists on a single channel. To define the convolution operation, what we need to define is what we call a kernel, which is an array of k by k elements, which has the same number of channels as the input image. And the way we compute the convolution is that we take this kernel and slide it through the image. And at each location that we stand, what we do is to compute a dot product. So it's a product by product of the elements of the kernel and the corresponding patch on the input image. Then we sum up everything, and that gives us the output for that location on the output array. So importantly, the kernel has the same number of channels as the image. We slide it through the image, and we obtain an output array that has a single channel in this case and the same spatial dimensions as the input image. In this talk, for simplicity, we will ignore all details about stride and padding effect. stride when you, instead of going one by one, sliding the kernel one by one, you jump 1 pixel or 2 pixels apart. And padding effect is when you reach the border, you have to decide what to do with the pixels that fall outside the image, the part of the kernel that fall outside the image, but we ignore these details because they are not relevant for what we are interested in. Okay. What is the nice thing about convolutions is that they allow us to capture different local patterns, the same way that we saw, or the Hubel and Wiesel saw in the primary visual cortex of some animals. And the way we do this is just by setting different coefficients for the kernels. In this example, we have an input image, and we apply, we run 3 different convolutions with 3 different kernels, and they result in these different images here. And what we see is that we are able to generate strong responses on vertical edges, on horizontal edges, or even in gradient magnitude. And just by we did that just by setting different coefficients to the kernel matrices. That's on one side. Another thing interesting is that in this idea of building mappings from D-in dimensions to D-out dimensions, now what we could do is to stack these 3 images, and we have generated a mapping from a single channel image to a 3-channel image, where the 3-channel images now has information about borders in the image. And that was not directly visible or so enhanced in the original image. And an important thing to observe here is that if we use, if we generated an image with 3 different channels, that's because we use 3 different kernels. So the number of kernels we use is associated with the number of channels we'll have as output. Well, that's okay, but we don't want to set these coefficients by hand. We want to learn them. So in order to build a model that we can tune, let's take a closer look to the convolution operation. And again, on this simple example of a single kernel over an image with a single channel. This expression here is just a dot product between, in order to compute the value corresponding for the output at the ij coordinate, what we do is to center the kernel on the ij coordinate of the input image. And we just, as we said, we compute the dot product between the kernel and the image patch center at that location. This sub-indices here is nothing else than a change of coordinates to work in kernel coordinates, because this sums runs over P and Q, which are the coordinate reference system for the kernel. And so this moves this ij, which the origin was here, to this location, and we can do and this sums makes no sense. So it's nothing complicated. Now, that with a single channel image, now what happens when we have images, input image with multiple channels, and we want to incorporate multiple kernels, because we know that modeling multiple patterns is useful for perception. Well, formally, it's pretty much the same. The only thing we have to do is to reinterpret each term on this expression. Now, what we have is that we will have, if we want to generate a D-out channel output, what we'll have to have is D-out kernels, each of which will have spatial dimension k by k. And in the expression here, what we have now is that this HPQ is now a matrix of D-out times D-in dimensions, with each row of this matrix corresponding to the vector centered at the location PQ of the kernel. So we have this matrix for each PQ location of the kernel. And Fij is just the vector that comes from indexing the ij position of the input image. And if we do this operation, what we have is a vector of d-out dimensions that will correspond to the dimensionality of the output we want. We sum up all the terms that arise for this operation, and we have precisely this output vector for location ij and the output grid. It might seem like a bit unnecessary to complicate things like that, but keep in mind this expression because we'll go back when we compare this module with multi-head attention. Now, to summarize, what can we say about convolution? Well, first, they model a local neighborhood, a local context, and this context is determined by the kernel size. If we want to model larger contexts, larger neighborhoods, we have to use larger kernels or do something I will talk in a minute. They are shift invariant, and what does it mean? Is that the response of the convolution operation won't depend on the location. If you have an object you want to detect within the visual field, it doesn't matter if the object moves within the visual field, you will generate proper responses respective of the location. And the only learnable parameters we have here are the kernel coefficients, which is something similar to template matching, which is related to correlation, and convolutions are two operations which are very, very close. And in terms of visual perception, if we use multiple kernels, we'll be able to capture multiple patterns. And this idea of hierarchical processing, we'll see in a minute, but if we look at the architectures, convolutional neural networks, wall convolutional neural networks, what we'll see is that there is a pattern of, after some stages of convolutions, what you incorporate is some non-linearities and some what is called pooling operations, which the idea of a pooling operation is to reduce the spatial size of some feature map. So you can take the average of 2 by 2 blocks and non-overlapping blocks, and then generate an array that has half the size of the input, of the original input. But we'll talk about that in a minute. Okay, now let's turn our attention, okay, to the multi-head self-attention module. The idea is to put it into the context of visual perception, but let's first start talking about sequences, because that was the context in which this model were proposed. This is the familiar transformer encoder decoder architecture. This is the transformer encoder, and we'll look at this module here, multi-head attention, which is enlarged here. These are modules that we will see as sequence-to-sequence mappers. Again, we feed one of these models with a sequence of embeddings. What we get at the output is a sequence of embeddings, of transform embeddings. And we can get some previous information from the name itself. The multi-head part of the module means that we will apply the very same computational module in parallel to the input sequence, using different configuration of the coefficients, and we'll then have to summarize this into an output sequence. And the self-attention part comes from the fact that to encode a single element from a sentence, from a sequence, what we'll do is to look at the sequence itself as context. We are not using external information as context, we are using the input sequence as a whole as context. Now, in multi-head self-attention, the first operation we do is a projection of the input sequence of embedding. By this block, I'm representing here a sequence of I don't know, 5 elements, each of which has dimensionality d in. And by these projections, what we do is to project these input embeddings into 3 different spaces by projection matrices WQ, WK, and WV, each of which has to be of dimensions d in times d. So at this point, what we have is 3 different views of the same input data. Once we have these 3 matrices here, we take one element of the query of the Q embeddings, and what we'll do is to generate a re-encoding of this Qi vector into a Q prime I vector by the following operations. First, what we do is to generate a relevance score between our input Qi and all elements of the matrix K. This relevance score is nothing but a softmax over the dot products between Qi's and the elements of matrix K, scale but the square root of the input dimensionality. Thus, di is the dimensionality of these embeddings that doesn't have to be the same as the input dimensionality of our original sequence. And once we have this n scores, different scores, all normalized up to 1, and we use them to compute a weighted sum of the elements of the matrix V, which was the other matrix we generated in the first step. Then we sum everything up, and now we have this embedding Q prime I for one of the heads. So we do this for all our attention heads. And what we do next is to just concatenate them all and project them back to a convenient output dimensionality, because this might be very high dimensional. And so we stack all these matrices and project and use a new matrix W to project them back to the out dimensions. And that's it. That's attention for sequences. So how does this work for images? Well, what we do is to transform images into sequences. And to do that, what we can do is to split the input image, any input image we want to process, into tiles, into patches, and arrange them into sequences. But now we have this, and now we can convert these patches into an embedding just by stacking all pixel values into a big vector, or by using a linear projection into this embedding space. And then we are in the situation that we talk about here. We can fit this transformer encoder, we can fit this multi-head attention layer with our images that comes from visual information, with a sequence, that comes from visual information. Now, important thing here is that is to remember that we can always map back one of these elements of the sequence to a particular location of the image, because there is a one-to-one mapping between elements and patched here. And this is important in some applications like segmentation or localization, where we want to preserve spatiality of the information. And as a side note, there was a paper in CVPR 18 of Hu et al. That they propose a very similar attention mechanisms that works on channels, and that was called squeeze and excitation networks. And this is one of the earlier attempts to induce attention in the computer vision community. Okay. Now, what can we say about multi-head attentions in the context of visual perception? Well, the first thing is that they are not local. They model global interactions. They allow to capture relational patterns between elements that are far apart within the field, the same field of view. This idea of attention, in the sense that what we do is to generate an embedding that arises from comparing the very same embedding to other elements in a neighborhood, is very similar to a self-similarity descriptor that were proposed 2007 by Schleckman and Irani. And the idea here was to model a given patch, to generate a vector, a description of this patch in terms of how similar was this patch to its neighbor. And this allowed to solve some very interesting problem at that time that were to compare different structure, different visual structure, even when the underlying texture and the underlying visual qualities were very different. And that was possible because by doing this self-similarity descriptors, by computing it, what we can do is to encode self-similarity patterns, which at the end is something very similar to what self-attention does. Okay. Regarding the invariances that self-attention has, is a permutation invariant operation. That means what means that is that if we shuffle the input sequence, we'll get the very same embeddings, because there is nothing here that reflects the location of the embeddings within the sequence. So if we want to have some information about the ordering of the elements in the sequence, or the location of the 2D patches within the image, we have to inject this information back. And we have our learnable parameters now are the Q, K, K, and V matrices, and the output projections, plus some additional MLP that we'll talk about in a minute. And this corresponds to these different projections of the input into 3 different subspaces, and the final projection matrix after concatenation. And in this case, the way we have in multi-head attention to inject or being able to detect different patterns will be by using multiple heads, multiple attention heads. And regarding hierarchical processing, we can do the same. We can stack this very same model one after the other. Now we don't have strong priors induced, like in case of convolutions. We have these very strong priors of using local operations, shift invariants, and the linear operations. In this case, we don't have this prior, so if we have to learn, so we'll have to learn them from data, because we know, because for what we know about visual perception, those priors are relevant. So at the end, we have to learn them. And the same pooling operations that we use in convolutional neural networks can be seen here as absorbed by the attention mechanism. We can see the attention in the last layer as a pooling operation of all the inputs. Okay, now that we saw the inner workings of convolutions and multi-head attention, we can see them as some encoding mechanism that what they do is they do a projection and an aggregation of some transformation of the input. We have here the expression for convolutions, and here the expression for self-attention, for the output, for the final computation of self-attention. The only difference here is that I restrict the indices to be in the neighborhood of I and j, because why not? We have, in the case of convolutions, we have that this sum goes over the kernel locations, and we can make this neighborhood to be forced to be a local neighborhood, or we can extend it to the whole image. So I think it's more general. Now, if we compare convolution to self-attention, in the case of convolution, we have a linear projection, which is the orange part, and a linear aggregation, because the projection is just this element that we saw is a matrix times a vector, and the aggregation is a sum, so it's linear. But in case of multi-head attention, what we have is that the projections, we have multiple projections now, which are all linear, which are given by this input query key and value vectors, but the aggregation is non-linear. And this is because of the existence of this softmax operation here. For convolutions, we have that diversity in the patterns we capture comes from the fact that we use multiple kernels, while for multi-head attentions, this diversity comes from using multiple heads. We can see convolutions as a patch-to-patch operation. Because of the way they are computed, you do a one-by-one product over the kernel elements and then aggregate them all. But this operation, in the case of multi-head attention, we can see it as an element-to-patch similarity or comparison. Because to encode a given input embedding, what we do is to compare this embedding against their neighborhood. And that is modulated by the attention mechanism. In the case of convolution, we have that the number of learnable parameters depends. We have, if we use D kernels, each of which has D input dimensions and K times K dimensions, we have this number of free parameters. And if we want, and the number of parameters depends on the neighborhood size, which is clearly because we have the size of the kernel here. But this is different in case of multi-head attention, because although the number of parameters scales also with D square, this is H is the number of heads. There are some simplifications here. The number of parameters is independent of the neighborhood size. And this might see an advantage in some cases. And finally, regarding the cost of generating a single embedding, both of them are squares. The cost is squared in D. But multi-head attention has the issue that in order to compute an embedding, what we need to do is to compute the attention matrix, which is of square of n, where n is the length of the sequence we are trying to encode. So this incur an additional memory cost, which is not present in convolutions. And sorry, this is one of the main limitations of attention mechanisms when dealing with high-resolution imagery, like very high-resolution images or satellite images and these fields, for example. Okay. Sorry. Now that we understood the inner workings of these modules, let's see how they integrate into full-ground networks. And I took two examples here, which I think are very good examples, which are ResNets and VITs. In the case of ResNets are built as a stack of residual blocks. And although there are many ways to write a residual block, this is one possible way. This residual block is a composition of convolution, some normalization layers, and nonlinearities. But important here is this thing, this connection, which bypasses this subnetwork, and this is the residual connection. It is what it allows us to train very deep networks with this architecture. In ResNets, what we usually do is to use these stacks of residual blocks and interleaved with this, at some point, we add this pooling and nonlinearity operation, as we saw some slides before. And so we are able to gradually reduce the spatial size of these residual, these feature maps until we reach a point in which we can aggregate them, build a single vector, and use this vector to feed, I don't know, a multi-layer perceptron that solves the task we are trying to solve. Well, for the case of transformer, what we have, in the case of VIT, sorry, is that, as we saw, a transformer encoder is nothing but a concatenation of this block, which is the transformer encoder. The only thing we add on top of this network is that in order to inject back, as we said, we have lost all information regarding the spatial arrangement of dispatches. So we have to give some insight into the model about their ordering. So we add what we call position embeddings or position encodings. And another difference is that we also use an additional embedding, an additional token here, an additional embedding that we use for prediction instead of aggregating all the output embeddings as we did with the output of the ResNet. So we use this particular embedding to feed MLP if we want to solve a problem for classification or regression or whatever. So, what are these position embeddings? Well, they're, as I said before, is the information that we inject back into the systems to account for the loss of positional information. And there are many flavors of positional embeddings. They can be all designed by hand. There can be you can compute a function that gives you a vector that encodes a particular location in some way, or you can learn them from data. The important thing of position embeddings is that they are independent of the content of the image. So the position embedding for a given patch will be the same no matter what where this image patch come from. And that's the idea of trying to encode the location. And okay, there are some, I mentioned you can use hard-coded encodings, you can use fully learned embeddings. There are some intermediate approaches where you can use a very simple encoding of the input location, like X and Y coordinates, and then use a projection matrix to transform this 2D representation of location into a D-dimensional representation that matches the dimension of the input embeddings that you use with your model. And okay, that's on position embeddings and some particularities on this CLS token. If you look back here, at some point we'll have to generate this. At some point, at all points in the network, we'll have to generate this encoding for this additional token that we term CLS. And if you go up to the end of the network, what you'll see is that you can see this initial token, the CLS token, as a refined pooling operation that is task specific, because on this embedding you will connect your prediction head. So what you learn from this embedding will be very specific for the task you are trying to solve. So it's a way of generalized pooling operation. But if you try with other pooling strategies, like doing average of the embeddings of max pooling, they might also work well in practice. Okay. We have seen now how ComNets and Vision Transformer works. They have their differences in terms of network construction. Perhaps the most important difference is that it comes from the amount of data you need to train them from scratch. I know we can always take a model pre-trained online, download it, and fine-tune it for our particular applications, but there are some scenarios where either you want to train a very specific model for your problem domain, or other cases in which the data, the images you work with have nothing to do with the kind of images other models were trained. Like, for instance, if I want to build a model that works on satellite imagery, it doesn't make sense to use a model pre-trained on ImageNet. And there is a big difference in the amount of data we need to train this model from scratch. There is also a difference on the performance we can reach once we have the data and the compute necessary to train them from scratch. In case of COMNETs, the models available are usually pre-training consists on supervised pre-training. The same for vision transformers, but in the case of vision transformers, because of the scale of the data set used, we usually have to rely on some alternative techniques to automate this labeling. And there appear some strategies like model distillation and or different self-supervised strategies that help us to deal with this scale problem. And well, I won't talk about this. So now, when we have to choose between COMNETs and transformers, there is no easy answer. It depends very much on the data you have available, on the scalability of your model, on your situation. There are some scenarios where COMNETs are the way to go, and if you can afford the compute, it's a good idea to try transformers. So there are no one over the other, but depends on the context, as always. And well, I think I won't have much time to talk about this, but let me go to the summary. Okay. Okay, final remark. Well, what I say, convolution and attention are different mechanisms to encode visual information that originate from different priors, from different ways to think this re-encoding of embeddings. And there are two modules that should be in your toolbox. You can discard convolutions because the new hot topic is transformers. And the choice of one over the other will be dictated by the application at hand. One nice thing about transformers is that they make very easy to work with other modalities, as long as you can convert your problem into sequences. And working with other modalities implies starting to work with other people. You can communicate with people of NLP and speech recognition, because it seems that everyone is using the same famous model now. And this is very nice to do because you learn a lot by interacting with people from other fields. And it opens up new applications and challenges and difficulties and opportunities. And one thing to keep in mind is also that with this new family of models, both in convolutionals and transformers, which are really scalable, and then that it means that they can leverage a huge amount of data to provide us, to give us models that perform very, very well. With more scalability comes more responsibility, because by feeding it more data, we don't have to lose sight at where this data comes from, or the processes that led to this data. So I think that is.
Thank you very much, Jorge, for the great talk.
Thank you.
We have time for a couple of questions.
Thanks, Jorge, for the talk. Very informative.
Thank you.
Perhaps besides convolutions and also attention, the loss function can also help for this problem. Particularly, contrastive learning has shown to be actually quite effective for pre-training large amount of data.
Mm-hmm.
Do you think, what is your take on that? Maybe the loss function can also be expressive enough to separate different classes?
Yeah, the idea, my idea when making this talk was to compare different ways of computing for visual informations in general. Of course, the loss function does matter when you think on solving particular problems, and it can matter a lot. Regarding what you mentioned, self-supervision, contrasting learning, there are valid techniques to train these models, but they will be built based on the same visual components. So, sure, yes, but I think the final message will be, okay, don't forget that these are modules to compute visual information, and although they are quite old in some cases, they are still useful and can be used to do the things we do now. Okay.
Thanks. There's another question in the back.
Hello, thanks for your talk. My question is with respect to the positional embeddings. And the question is, why do you need those embeddings? I mean,
why
do we need embeddings for encoding the position? I mean, usually we think in terms of embeddings when we want to put things of high dimensionality into something lower. But here we have like X and Y telling the position, or maybe Z, and then we try to learn from those an embedding which looks like more complex. So why do we go to like greater dimensions for the position?
Okay, the idea of the positional embeddings is because of the definition of these attention mechanisms. You don't have anywhere here something that relates. Sorry, here. When you feed this sequence, you will feed the sequence to an encoder that doesn't matter on the order of this input sequence. And in both language and images, in the case of language, positions seem to matter, but in images it matters a lot because essentially our images are information arranged spatially. So you have to capture, or you want to capture this spatial dependence. Of course, in some problems we have more impact than in other problems. Probably in some problems some location doesn't matter at all, and you don't gain much by inducing position embeddings. But I think there are a reasonable way to inject back this information you lost by partitioning and sequencing an image which is a 2D array. I don't know if this answers your question.
Yeah, but my point was, why to build embeddings out of positions and not to use just the raw positions?
Why? Sorry, didn't hear well.
I mean, you say that you can learn the embeddings.
Okay, this one here.
Yeah.
Okay.
So why to learn such a representation in a great dimension, instead of using just the scalar X and Y, which tells exactly the position of the patch?
You learn an embedding because it's the way you combine the embeddings to the input sequence. Look here, sorry. No, here. The way you inject this information is by adding these position embeddings to the input embeddings. So you need to have an embedding of the same dimensionality of your input. So that's why you learn an embedding.
Okay, thanks.
Okay.
So I think we have time for one more quick question.
Could we maybe, thanks for the talk first, very informative. Could we go back to the slide where we see the way it is cut up in patches?
Patches? Here.
Yes. So I'm wondering if you can feed, or do this in a way in which you take into account semantic components or something that makes this part more efficient, knowing that not everything in an image is useful. And when you have information about the domain,
I'm sure that has been tried.
Yes. Do you, could you speak about that? Or?
I don't know. I'm sure it has been tried. I can't remember the paper now, but the idea was to run a segmentation algorithm to build a graph on the segments and then to build to transform this graph into sequences. But then you face the problem with this pre-processing, which might be too complex to the gains you get at the end, and maybe just splitting the image into regular patches and using lot and lot of data, you get the same performance.
Okay, thanks.
Thank you. Yeah, I think we have a lot of questions left, but we are running out of time, so maybe you can address the question later to Jorge or meet him and have a chat.
Thank you. Thank you very much.
Again.
Hello, can you hear me well?
Okay, hello, good afternoon. We are very pleased to introduce the sponsors talks. As you know, we have to thank them a lot because this event couldn't have been possible without their support. So the idea is that in the event we have these slots of time in which we can have our sponsors to tell us what they do or what they are working in. So in this session we're going to have three talks. The first one is by Germán Capdevrat, that works in Ceibal. He is also a professor here at the University in the Faculty of Engineering. So Ceibal works with education and technology, and I guess he's going to tell us a bit more about what they do. Thank you, Germán.
Thank you, Pablo, for the introduction. Well, thank you for the applause. Good afternoon, everyone. I'm really happy to be here. I was lucky to be here also in 2019, and it was a wonderful experience. So I'm sure this one will be great also. For those who come from abroad, it's really a pleasure to welcome you here in Montevideo. And I want to thank also all the organization committee, and it's great your work for making this possible. And one thing that I remember from that time in 2019 was that the weather was fantastic. And this week, it seems that it will be quite good again. So I guess that the committee must have quite good AI models for weather forecasting. Let's move on, we don't have much time. Ceibal started more than 15 years ago as the one-to-one education program implementation in our country, in Uruguay. The main goal at that time was to bridge the digital divide. And many time has passed from that early years, where the main challenge involved the delivering laptops to students and deploying Wi-Fi at schools. And nowadays, it's a bit different. Ceibal is established as an innovation agency regarding technology applied to education. And I dare say it's also a well reference in the area. For example, last year it was included in the case studies of the Harvard Business School. So Ceibal has changed what a classroom might look like today in our country. And I believe we have gained extensive experience introducing education into the public education system. Ceibal covers the whole, all the primary and secondary schools in the country. So if you want to check the numbers, we have a stand here. You can look at the website also, there's a lot of information. But our golden triangle consists of these three main points. Devices, as I mentioned, every student receives rather a laptop or a tablet, but we also have robotic kits or special devices for children with particular needs. So that's one of our pillars. The other one is, of course, connectivity. We need internet access at school, so there's a lot of infrastructure for that purpose, Wi-Fi access, and also other kind of technologies, for example, video conference equipment for remote teaching that we will see next. And the third one, it's about contents. And I use the term contents here in a broad sense because as we will see in the examples, we have, for example, standard content which relates to education platforms. We have a main learning management system, but also a couple of platforms for math, one for language, one for English teaching. There's also a digital library, which is also available to all the population in the country. But content today for Ceibal, it's also about a lot of activities. For example, we organize every year the National Robotics and Coding Olympics, which final event is this one that is shown in the picture. We have several workshops and courses for students and teachers. So it's much more than traditional content. A lot of people in Ceibal works for those activities every day. For example, here we have an English lesson, which is given from a teacher who is abroad our country. That was an innovation to tackle with the lack of enough teachers here in the country for the universalization of English teaching. So this one was before the pandemic, so at that time it was quite particular to have classrooms from a teacher that is not present in the classroom. And this technology was quite successful for that purpose, and is today being used for other activities, such as a computational thinking program, or sometimes for activities, for example, scientists or artists that connect to several classrooms at the same time and talk with the students. So we are in an AI event, so I have to say something about AI in education. And when I prepared this talk, I came up with the idea of riding into the future, thinking about AI as a powerful horse that could indeed help us in order to generate better education experiences and learnings. But as horses, we have to first tame them in order to use it to ride properly, advance at a safe pace, and going into the desired direction. So I believe that AI, of course, has to be used ethically and responsibly, and we have to advance with caution and careful planning in all areas, but in particular in the education. And just to finish my talk, I will just mention some of the projects that we are involved right now at Ceibal. We have recently started this journey, so we are working with the community, with you, with a lot of people from the academia in diverse areas. I cannot go into the details of each project, but we have things regarding adaptive learning. We have things about smart assistants or recommendation systems. We are also working on learning analytics. We have some particular areas involved in introducing basic AI concepts at early ages, primary and secondary schools. And just to name a couple of the last one, we have some examples of automated assessment, and also a very nice project that we have with Pablo about classroom activity analysis. So I want to highlight that this work is all in collaboration with the academia, with the research community. So I just going to end up my presentation with a straight call to action for you. The first point is to encourage you to work more on AI applied to education. Yes, we need that. And the second point is, of course, that you can talk with us. I would love to discuss with you ideas of projects. We have lunch times. We have the breaks to. So just contact us, and we will be glad to collaborate. So thank you very much for your time.
So thank you, Germán. I think we have room for one question. So if someone has anything to ask, no. Okay. Okay, over there. Can you?
Luciana, allá atrás.
Okay.
Hi.
Yeah.
Do you collect any of the data that happens when the kids interact with the tablets or the laptops? Do you keep data sets?
There are different cases. In some cases, we collect some data, and in other cases, no. So it depends on the particular application. What is important that in any case, we have like the typical terms and conditions, or if it's something that particular for any research project, we have to do in that case the particular authorizations from the parents or things like that. So,
thanks.
But yes, there are some cases that we do that.
I was thinking of that, yeah, creating like a data set specifically for research.
Mm-hmm.
But it would require specific terms and conditions, you're saying.
It depends a lot on the particular case. Because in some cases, it's just like typical performance stuff, for example, things about the network or the device operation. And in other cases, you have like private data involved, so.
Okay, thank you very much. Yeah, and okay, the second talk is going to be given by Matias Tassano. He's a former member of our Faculty of Engineering here. Now he's working in Meta, so he's going to tell us some of the work he does in the Meta Reality Labs in Zurich. So thank you, and we're glad to have him here.
Thanks, Pablo. Hi, everyone. Very excited to be here, despite the jet lag. Very happy to be back in my hometown and in Khipu, and in my alma mater as well. So yeah, we have only a few minutes. I wanted to discuss how we use AI in my team, in Reality Labs. Yeah, in particular, I'm going to talk about how we use AI to enable really tiny cameras for augmented reality. I'm sure most people here have heard about augmented reality glasses, AR glasses. But how exactly will that look like when we get there? So normal glasses enhance vision, the acuity of vision at every moment. But what if AR glasses could also enhance perception in other ways? So it's been predicted that in the future, instead of carrying smartphones, we will wear stylish glasses like the ones in the picture. And these glasses will offer virtual reality, they will offer augmented reality and everything in between. And also the virtual and the real world will merge according to our needs. But what kind of things do we imagine? So what if these AR glasses could, for example, enable my low light vision and help me see better at night? Or what if they could help me bring my loved ones closer to me, even if they are on the other side of the world? And for those who experience some loss of vision, what if these glasses could help them recover some of the eyesight? So to achieve those goals, we need to do AI, and we need to do on-device AI, meaning we need to do AI on the glasses themselves. There are also many other reasons why we need on-device AI. Just to mention a few, we have privacy concerns, we have latency, think about connectivity. I want to roam freely with my glasses and not having to worry about being connected to the internet. Also very important, energy. So doing on-device AI efficiently is very important to meet energy constraints. So we have clearly these glasses we see here. We'll have cameras, right? AR cameras. But different challenges for these cameras, right? One of them come from this social acceptable form factor, right? So we want stylish glasses, right? We don't want really bulky kind of VR headset style glasses. We want glasses I want to wear anywhere at every time. So lots of problems come from this form factor I talk about. In particular, these glasses are small, so we have a small room to fit sensors, right? So my sensors, my camera sensors will be small. That means the frames, the images I can capture with them will be noisy, will not have much excellent quality. We'll have small resolutions as well. Also, the glasses will be small, so I'm going to have small batteries. So I have to consider how I use power. And yeah, thermal limitations. I'm going to be wearing these glasses on my head, right, next to my temples. So I cannot just pack any state-of-the-art algorithm in there, because I have to be very conscious how I use compute in a product like this. And of course, on the other hand, we have expectations, right? So I would love to get really high quality videos and images from these glasses, and I don't want to charge them every 1 or 2 hours. I want the charge to last for a whole day. And I also want them to support perception tasks in the wild. So all this will shape the algorithms I can pack in these glasses, how I'm going to design them, right? So For AI, we use AI for camera imaging. We just mentioned the limitations we have in the sensor. So small sensors means small pixels. So it means less light, so high noise. So we're going to need really good denoising algorithms, right? Also, we have fewer pixels, so smaller resolution. So we might need algorithms to super resolve these images. So what we do is we try to bridge the gap between having small sensors and large sensors with AI. And that includes different tasks, including, for example, noise modeling, right, for the sensors. Very importantly, a co-design between AI and conventional imaging algorithms. So, for example, we see an illustration from a publication of mine, which is a video denoising network, right? Which is state-of-the-art, but runs orders of magnitude faster than similar algorithms. Yet for the glasses, for the AR glasses, we need to do better. So just to give you an idea of how challenging this problem is. And lastly, we also have the concept of designing the hardware to support certain AI operations. So designing hardware and software together is crucial to attain efficient AI, which in our problem is very important. So yeah, not many companies in the world can do that. Luckily, Meta is, so that's how they do in our team. Okay, time's up. That's been all I wanted to talk about. Hopefully you enjoyed the presentation.
Okay.
Thank you.
Thank you, Matthias. I think again we have room for 1 or 2 questions. So if you're interested in asking something, it's the moment. Oh, maybe I have a question, but it's about like the technology to be able to see things through. It's like, is there anything challenging about that? That is,
yeah, of course.
Already solved or on track?
Nothing is solved in this. It's all work in progress.
Because to not make it bulky may be hard.
Yeah, exactly. So, yeah, the problem is you can use something like LEDs, like Google Glasses used, and there's another product by Xiaomi, I think, that has been, brought into the market recently, and they use LEDs, but that might be bulky.
Okay.
So yeah, that problem hasn't been solved yet. Okay. OLEDs is one way to go.
Okay.
But yeah.
Okay. Thank you. Thank you for being here again.
Dale.
Okay, and the third and last talk of today, of the sponsors, will be given by Ruben Char. Ruben Char is a professor here at the Electrical Engineering Department too, and he works in ADME, which is one of our sponsors, which has a great responsibility in managing the dispatching of energy that is produced in the different sources in the country. So he's going to talk about some of the work they do to put some artificial intelligence in
¿Sabe cómo hacer que aparezca acá además?
Tendrás que poner las propiedades de...
Pero ya tenés que capaz que mirar eso. Espejo, dale ahí. Aplicar, lujo. Pero para que...
Okay, we start then.
Well, good afternoon, everybody. Thank you to be here. I will show you in which we are using AI at my work. First, I must apologize for my English. It's really bad, but I will try to do the best. Well, one of the principal works at ADME is perform the optimal dispatch of the energy resource of the system. That is, every time, every hour, say what resource must be dispatched to guarantee the fulfill of the demand at the minimum cost. The Uruguayan system, as you can see there, is 50% hydropower and the other 50% renewables, wind, solar, and biomass, and very few thermal energy in the system. This is important because you have a system with huge stochasticity, huge random component. It is very important to the application of AI in our show. Well, the optimal dispatch of the system is a dynamic programming problem, as you already know. The Bellman in 1957 published a method to compute the optimal solution, the Bellman recursion. In the same work, Bellman states that his method have a problem, the curse of dimensionality. Today we call the Bellman curse of dimensionality. Today at ADME, we have two robots using the Bellman curse to solve the problem of dispatch. One of the robots look ahead 3 months with a daily detail and publish in our site twice a day the results. She look ahead 1,000 of possible scenarios and compute the optimal dispatch with a daily detail. The other robot take care of the short term and look ahead 7 days, a week, with hourly detail. These two robots use Bellman recursion, classical Bellman recursion method. So we are condemned to not improve our models, incorporating new state variables or random variables. To escape from Bellman curve, we implement another generation, second generation of robot with AI. The robots are running in parallel with the first generation. The concept is very easy and known for you. An agent that explores the future by simulation with the data collected during the exploration, improve the value function of the state value function of future cost function, and perform another simulation. We have a very detailed model of the system, and the agent use the detailed model to simulate the behavior of the future. this is what we implement. The structure of neural network is an array of neural network, one per step time. The robot that look ahead 3 months have one neural network per day. The robot that look ahead 1 week have one neural network per hour. And they are continually exploring and improving his representation of the goes-to-go function. The special aspect I need, I think that the important thing for you are the special, the key aspect to implement AI in this field of engineering. The first one is that for the optimal policy, the information is in the derivative of the goes-to-go function respect to the variable state. It's the difference that the important are in the different value of the value of the state of the value function, and not in the value itself. The second is this is a very noisy system due to the renewable resource. So you are trying to collect information about the difference of two random variables when you are looking forward to the goes-to-go function. You need a technique to reduce the variance of the information. This is a special key in this field of application. We use common random number, that is a classical technique to variance reduction in Monte Carlo simulation. Due to the use of common random number, we have a problem, because when you simulate a system, different trajectories, but with the same input random variables, the trajectories converge and the exploration lost the capability of explore. So we need other technique, and we break the natural evolution of the system time for time to explore the state of the trajectory in the state space to recover the exploration capability. Well, another important key in this application is that we are solving the problem in a continuous time, because the system must be operated at a continuous time, so the robots are learning continually. And they acknowledge they gain in a time are not lost and continue in the next time. That's all.
Okay, thank you, Ruben. We also have another time for one question. Yeah, Matthias. He's going to give you the microphone.
Thanks for the talk, very interesting. I'm not sure if you mentioned that, but I was wondering, so the network has a lot of renewable energy, right, capacity being used. How much more difficult is the problem you're trying to solve with this, with renewables? Because they might not be available at all time, right?
You are referring to intermittence of renewables.
Exactly.
It's not a problem. It's not a problem because we have a very big hydropower system, and the reservoir of the lakes of the hydroelectric filter the variability. The more important variability here is the rain. We have years of drought and years of rainy years, but you don't have years without wind or solar radiation.
Okay.
It is difficult to filter the heavy signals.
Okay, thank you. Maybe one more? Yeah, okay.
The actual system in Uruguay, we are leading with 6 state variables and a lot of random variables. But with the new algorithms, we have simulated Brazil, Argentina, Uruguay, Paraguay together, near 70 state variables.
Okay. Thank you very much. Thank you, Ruben. It was a great job, and it's very important. Now, just stay a couple of minutes because there will be some announcements about the practical sessions.
Yeah, we changed that. So it's only to tell you that we have the coffee break now, and the coffee break will be lasting until 15 minutes more because we are a bit delayed. So we will start the research talks at 4:15, okay?
And the other announcement is like the posters that are from the day of today. If you can keep them there until tomorrow morning, great. So if someone else wants to go and have a look, and then tomorrow at noon, a bit before noon, please take them out because the poster session 2 will start and we need the room for the new ones.
Couturi received he graduated from ENSAE in France, and he received a master's degree from ENS Paris-Saclay and a PhD from École des Mines Paris. He was a postdoctoral researcher at the Institute of Statistical Mathematics in Tokyo, where he held positions in Princeton University and Kyoto University. He's a professor at ENSAE, and more recently, he was with the Google Brain team before joining Apple's machine learning research team. So it's a pleasure for us to have Marco here for the first time, I think, in Khipu. So give him a big welcome to Marco.
Thanks a lot, Pablo. Thanks a lot. Really a big thank to the organizers, because I organized in the past this kind of event in the previous life, and I know it's very exciting, but a lot of work. So really thank you very much for all you've done to assemble this great community. So today I'm going to give a talk about optimal transport. So Joan this morning mentioned in some slides something about Wasserstein distances. If you know about them, this will be about this. If you don't, I will try to give you a smooth introduction. And I will finish in the end about some more recent work. I should maybe say submissions. So this is very recent things. So let me just say that this is joint works with people at Apple, Michael Klein and Pierre Blanc, who sit next to me in the office, and Théo Ushida, who is at ENSAE IP Paris. So I will start with the simple puzzle. Imagine you enter the room, okay, and the light is off, and then you turn on the light, and then you see some particles, okay, this is 3D. You see 6 of them, okay, and then someone actually turns off the light without you noticing, and then you just turn it on again, and you see 6 particles again, but in a different configuration. And so the idea here is what happened basically, between the time I turn on and off and on again. And so I'm going to label what I saw afterwards with yellow and what was there before as blue. And here in this case, those are really, you can imagine like particles, molecules, whatever. You can't really distinguish them. You were not able to tag them. So if you want to find out who went where, you have to make a guess. And you could guess that this is the way the blue particles arrived to the yellow particles, but that it is not very intuitive somewhat. You would like to find something that is a bit more low energy, let's say. You spend less energy to make this transition, this movement. And so instead, what would make more sense, of course, is straight lines. In a way, you could imagine that the particles have just started from the left and arrived to the right. And so I have a question for you. There are 6 particles. I drew here 6 lines that connect a blue to a yellow. And just out of the top of your head, is it easy to figure out how many possible ways how many sets of lines I could have drawn? When I chose 6, maybe I overdid it. So if it was 3, maybe it would be a bit easier. But it's basically 6 factorial, right? There are 6 factorial ways, 6 times 5 times 4 times 3 times 2, 720 possible ways of coming up with those red lines. So what optimal transport theory is about, at least one of the goals, if you want, is to come up with something that would look like the cheapest, in a way that we'll define later on, or a natural way to move the points. So one of the motivations of the theory is to think really in terms of, maybe gases or some configuration of things somewhere. You see them later somewhere else. You don't know exactly what happened in between, and you try to find something that is plausible. One of the other byproducts of this theory, and this is what Joan was alluding to, is that the length of those arrows, if you sum them up, you get something called the Wasserstein distance between those 2 sets of points, those two families. And one of the other important goals in this theory overall is to think about out-of-sample extensions. Here it was simple for me to, have those 6 lines. Maybe you could have yourself, drawn something that would have looked like those green lines, which I will explain how you get to them. But the idea is, if I get a new point, am I able to find a likely place where it would land? So this is some of the ideas. So let me just introduce a bit more of math and try to be a bit more formal here. So I'm sure many of you saw this before in a CS like 101 class. It's the matching problem, right? What I was describing, using the permutations was essentially a problem would have here 5 blue points and 5 red points. And I am trying, given a cost function that gives me, you know, how easy it is to associate, let's say, y1 here to x1 here to y3, gives me a best possible permutation. So usually you will come up with, again, 5 factorial possible permutations here. And the way we will score the quality of a match is by this simple objective. We will see later that there's other possible objectives, but this is like the starting point of optimal transport theory, where you're just going to sum a cost. So for the purpose of those slides, the cost is more or less the distance, but you could imagine something a bit more fancy. Between xi, matching xi to y sigma I. And then you can see that this cost, again, is what I was telling you earlier, is essentially a sum, if the cost is the distance, of the length of those arcs. Now, there's many such permutations, as we said. I would like to make a small parenthesis to say that you're probably also familiar with another type of matching, which is, let's say, nearest neighbor matching, where you would match all of the red points, each of the red points to its closest, you know, blue neighbor. That's like the anti-optimal transport. It's like it's the case where you don't care about having something that would look here like a bijective map, or that would be such that you're well distributing, you know, all of the red points towards all of the blue points. And so I'm saying it's the anti-perspective, because it's important, I think, to keep that in mind when you look at, you know, those Wasserstein distances, etc. It's important to remember this is not what we're doing. We're really trying to recover somewhat all of the blue points from the red points. And this plays an important role in practice. And this can be mitigated in practice, but this will be for another lecture. By mitigated, I mean something intermediary. Now, let's go back to the problem. As I was saying, the best thing you could do here is to find a permutation which does the job of minimizing this thing. And here it's, of course, easy to, you know, visualize it. It's, let's say, the first one where x1 is mapped to y1, x2 here is mapped to y3, x4 or x3 here is mapped to y5, etc., etc. Now, I have, you know, started this with a puzzle, and I told you about, and I'm trying to tease your brains here, but what is this used for? So historically, this has been used a lot, let's say, from World War II to do optimal allocation of resources. So a canonical example here is, imagine you're in a space where you're describing either the physical position of workers or a feature space that describes the skills. We have 5 workers and 5 tasks. How do you allocate a task per worker? So this is giving you a fairly good answer. The other thing that I was mentioning is, if you start thinking about those red points as samples from a distribution and the blue points as a sample of another distribution, then the solution, this optimal cost, gives you this Wasserstein distance. And again, I will give you again this example where I have the particles before and after, and I'm trying to figure out, you know, a way of getting from the blue to the red that would be, from the red to the blue that would be more likely. So all of this is just eye candy for now. What about computing this optimal permutation? Well, this optimal permutation, you can find it if you make no assumptions about the cost. You can find it using something fairly old. So it's called the Hungarian algorithm. People forget about the names of the people that actually derived it. This was rediscovered by Kuhn in the 50s, but he called it Hungarian because he knew that 2 other Hungarian mathematicians had actually more or less proposed the algorithm. And so we can do it. You know, we can compute those when n is, let's say, 1,000. We will be able to compute those optimal permutations. But of course, this is more or less the limit. You know, it's not working so well. If optimal transport was only about this, then we wouldn't have heard about optimal transport. What makes this limited is that, as you can immediately see, if I give you, let's say, another family of points which is 6 points instead of being 5, like there's a 6th blue point, then I'm lost, right? Permutations are easy to deal with when the number of points on both sides is the same, but as soon as I add you a 6th one on the blue side, then I don't know what to do. The other one, apart from maybe discarding it. The other problem is the out-of-sample extension that I told you. What happens when you give me a new red point? Where would it go? And the third thing, of course, is this computational cost, which for machine learning would be prohibitive. So we have to, although this is very intuitive, we have to move away from this. And if we want to move away from this, first, we need to handle different situations, more general ones, so where we will have different numbers of points, or even weighted numbers of points. So by weighted, I mean here, so this is what Joan was, if you remember this morning, he showed some arrows. At some point in his talk, he said, I'm moving away from points to points with arrows. So this is just simply the idea of moving away from points to Dirac masses, and Dirac masses with weights. So I'm just giving myself more generality, and what I will explain is how to somewhat generalize the idea of permutations to something that is sometimes called in the literature generalized permutations, but it's mostly called optimal transport plans. So here you can see, of course, that the model of permutations doesn't compute, doesn't compile anymore, because the weights, if you assign, let's say, this weight to something that is bigger or smaller, it doesn't work. So how do we do this? And this is something that was proposed in the 50s. We basically try to come up with a model where we're going to do a bit something like permutations, but a bit more general, where we're going to line up all of the weights of those red points, all of the weights of the blue points, and we're going to come up with a matrix now, not with a permutation, where we're going to keep track how much mass from this point is allocated to whom. So here you've maybe seen this, but I took a bit of mass from here to there, a bit of mass, the remaining mass from here to there. And so this means that x2, the second line, is sent to x3 and so y3 and y4. And then we just start making this kind of splitting, where we split the mass of each of the sources to deliver mass at each of the target points. So mathematically, what is particular about this? So we switched from a permutation, a binary, combinatorial object, to a matrix. The matrix has as many rows as the number of sources and as many columns as the number of target points. And what's specific about the matrices that we're going to talk about, those transportation matrices, is that the row sums of those matrices must be equal to what you gave me. So for instance, if you think that a standard analogy is to think that maybe the red points stand for bakeries, that have some production of bread, and the blue points stand for restaurants that need to serve bread to their customers. And the size here is how much bread is produced or needs to be delivered. And so here you can just simply see that this means that this second bakery is delivering its production to the third and the fourth restaurant. And so it's natural that the bakery's total production capacity here has to match what it sends to whatever restaurant it's sending mass to. So those we call the mass conservation constraints, and this is the same idea of it extended of the permutations, where we need to match one-to-one. Now it's natural to formalize now what would be the best possible transport. Again, as just saying, I am going to look at every pair of source to target, Pij. I am going to weight that by the cost of sending a unit of mass to xi to yj, so a bit like the permutation, but more general. And I'm just going to make this big sum here. And just as a historical reference, this was proposed by Kantorovich and Koopmans, and this is the Nobel Prize in economics in the 70s, 75. Now, how to compute this? Well, the standard way to do this is to use something called a mean cost flow solver, or typically a network simplex solver. And we remember one of the downsides of Hungarian was it was cubic. This is still cubic, so it's not a lot better. However, with this continuous model, we can try to our hands on something a bit more creative to have a trade-off between optimizing this linear program and having something faster. And so one standard way of doing this is to use what people call the synchrone algorithm, which is to regularize this linear program, which before, remember, was only about summing Pij cost xi yj, by the entropy of the coupling P. And so this technique, this, if you want, hack, basically helps you go a lot faster, which is more of the order of quadratic scale. So this is an order of magnitude, of course, faster. And there have been, and I have been working on with colleagues, on approaches that can now even rank to, can even go to larger sizes, because we can use some low rank assumptions on the coupling P. So now this takes me to the next general extension that I was alluding to, which is this idea of out-of-sample, extensions when you're computing optimal transport. So, in the beginning, I was giving you points that were basically there, just describing discrete measures. What happens when you're giving a distribution? And what would be the natural extension, when you have an infinite number of points of what a permutation would look like? Well, in that case, the natural extension is a map that is able to send, if I give you every point x that is in support of the first measure, I'm just going to give you a point t of x where it should land in the support of the second measure, and I will have to give you an entire map. You could almost look at this as a gradient field, which for every possible point in the support of the third measure has an instruction on where it should go. And this is really the limit of this permutation model. This, computationally speaking, is a lot harder. And this was proposed by Monge. So as a paradox, this was the first definition of optimal transport in the late 18th century, in 1782, and the hardest. And there's been a few very important results in the math community. So I won't cite today like Fields medalists like Villani or Figali, but I just wanted to mention two important people in this community. So one is Yann Brognier, who proved the theorem I will explain in a few seconds, and the other is Luis Caffarelli. I'm not going to cover his work, but he's one of the most famous Argentinian mathematicians, and he has worked a lot on something called regularity theory. So this problem sounds very, very, very hard. It's essentially trying to find, so if you think about even generative models, what is a generative model? It's something that tries to take something in low dimensions to a higher dimensions, tries to cover a target measure. So here, this is only the constraint. You just start with, I want to have a map that sends exactly the red to whatever is in the blue. And not only that, I want that it minimizes, on average, the length of all those green arrows, this infinite number of green arrows averaged over the source measure. So this is hard, as I said, but there is an insight that was proposed by Brognier in the 80s, which is that if the cost is a squared Euclidean distance, then there must exist an optimal transport, like this green function here, and it has to be necessarily the gradient of a convex function. So a function that is convex is from Rp to R. Okay, it maps a vector to a number. If you compute the gradient field of a convex function, it will, of any other function, it will map a vector to a vector. So that's already quite, it kind of compiles in my code. And so I will then, what Brognier tells you, you can only focus on gradients of convex functions. And there has been other computational approaches, but they only work in small dimensions. So one of the exciting things is that in recent 2 or 3 years, people have used this insight to say, oh, I know how to parameterize a potential that is convex. There is a duality that I haven't got the time to explain that tells me that this potential here, that is whose gradient is the optimal transport, has got to solve some optimization problem. And so here, I'm sure I'm confusing you because there are two different stars here. There's the F star, which is the best possible dual potential, and this F star, which is the Legendre transform of F. I won't go too much into the details, but I just wanted to say that this is an active area of research. And the last, to give you this overview a bit of optimal transport and what's going on in this field and how it's used in many domains, even like in genomics being one of them, but in the domain adaptation or also generative models, is that we can also extend the notion of matching to points that lie in different spaces. And the reason I want to highlight this is also because this is a great Uruguayan, Facundo Memoli, who proposed it, or who actually formalized it better. And so here is the idea. Imagine I want to match those two sets of points, the red points and the blue points, and they live in different spaces. So I don't have a natural notion of cost, to tell me how costly it is to go from this point to, let's say, any of those blue points. What I will do, what I have usually, though, is a way to say how similar points in the target, in the source domain are, and how similar points in the target domain are. It's easy to get a geometry, in each of the respective spaces, but it's difficult to have one across spaces. And in that case, what Facund and other people have been studying is this idea of, well, I can still try to think about matching, a text to an image, as long as somewhat that matching is a bit isometric. So let me explain what I mean by this. It means that if I am going to match x1 to y3, and I am going to match x2 to y1, then I expect that this matching does not induce a distortion in terms of the geometry. Which means that if, for instance, the association, the match between I and j is very strong, and I prime and g prime is very strong, okay, like 1, 3, and 2, 1, then I'm expecting that this difference in costs or distances squared here is small on average. And so this is a NP-hard problem, but it's been used a lot in various domains, in graph theory, for instance, and it's called the quadratic matching problem, but you can generalize it to those coupling matrices. Just a parenthesis on how you usually solve this. You just basically linearize this. You linearize this energy. This is called Frank-Wolf in optimization. You linearize this energy, and you call a linear optimal transport solvers of the sort that I just described iteratively. So you update PT plus 1, and you put it there to compute the gradient of this quadratic energy somewhere, and then update again. And again, here where I would like to say is that the computational picture has improved significantly in recent years. I'm going to make a plug, one of my students, Meyer, who basically showed that using a low rank assumption for the couplings and also a low rank assumption for the cost matrices here, we can be linear in the number of points of those two respective point clouds. So this means that we are routinely now doing Kromov-Wasserstein matching, quadratic matching for, let's say, point clouds of size 200 or 300,000 points. So the good news, if you're interested in this, is that you don't really need to believe me. You can actually test those tools by yourself. We have implemented them in a toolbox that we call Optimal Transport Tools. And the name is OTJAX because it uses the JAX framework, which it's very much to my liking. I like it a lot as a mathematician / machine learner. I think it's a very nice framework, and I know you will have a practical session. Some of you will have a practical session on JAX, OpTax, Haiku, and CNNs, if I remember correctly. So in a word, why is JAX nice from a mathematical perspective? It's because it's functional. I know PyTorch has a functional now layer, but I think JAX really did this in a slightly better way. I'm not working at Google, so it's even easier for me to say it. So the difference, if you want, is that in PyTorch, usually what you would say is get a computational graph out and call a gradient, on this result to get a gradient, whereas JAX is about computing a function, there is the gradient of f, not computing, but like instantiating a function that is the gradient of f and applying it on your input. So it's a bit like writing f prime of x versus f of x prime, which, as every high school student knows, is wrong. So if you like math and programming, JAX is great. And OTJAX has been developed on top of JAX and implements all of these ideas that I just described. It's currently maintained by folks at Apple, but we are receiving regularly contributions from Meta, especially, and from Google, and also from academia, different backgrounds. So, yeah, this was a picture that I wanted to add. This was we did a hackathon with half of people from Apple and half people from outside last month in Paris. So today, I'm really probably running short of time, but I'm going to push a bit the accelerator and describe two recent works that we did, now that I've laid out the basis of this theory. To describe two recent works, I'm very excited about both, so I will try to cover them quickly. And what those works build on, essentially, is on the idea that all of what I've described before actually works. We can now have a stable implementation that is reliable for this. And I'm going to present something that is a bit in between those two things, but more like on the right-hand side, which is trying to compute Monge maps. So the first, one of the great motivating examples of this field right now, apart from others that I won't have the time to mention, like Schrödinger bridges, or Joan was talking about them this morning, is single-cell genomics. So I'm not a biologist, but let me just try to explain my understanding of what this is doing. Imagine you have a patient that has cancer. You take a biopsy of that patient's tumor, and you have some cells. And ideally, what you would like to do if you want to do personalized medicine is to apply a drug on those cells and hopefully see after a few hours what happened to those cells. And you would like to understand out of those cells, basically, what happened to that cell after I gave it a drug. The goal is to be able to differentiate, depending on the cell. Hopefully, a medicine acts differently on your cells, whether they're tumor cells or healthy cells, right? This is what you hope. And so this is the goal right now, is to be able to have this understanding. The great news is that we have the tools at the level of each cell to understand what a cell is doing, what kind of genes are activated or transcribed at any point in time. If you just pick one of those cells, you will get out of that cell basically a RNA-seq basically vector that describes across 35,000 genes which ones are currently activated. The bad news is that when we pick one of those cells, we kill it. We have no way, if you want, of looking at a cell, seeing what's inside it, putting it back, giving it the treatment, and then looking again what happened after the treatment. This is something that's not possible because the measurement process is destructive. So what people do, of course, as you can imagine, is they pick, a few hundreds or thousands of cells before, a few hundreds of thousands of cells after treatment, where the treatment was given to all of those cells, and they try to realign them to figure out, to guess what could be, a possible effect of the drug depending on the cell type. And this is exactly what optimal transfer has been used for. This is what optimal transfer has been used for. Yep. So this is what optimal transfer has been used for, and exactly what I just told you. Let's try to find something that looks like the effect, of this drug. So I'm going to call it T star, of the drug, and that is going to recover from the starting cells all of the cells after the drug, and is going to give me an out-of-sample extension so that I'm able to predict for any cell the effect of that drug. So here is RNA-seq data. So it's the original measurements is a vector of 35,000 genes that basically measures for each cell the gene, how much of that gene is transcribed. So you will have some genes that will be working hard, some are not working at all, and you would like to understand after the treatment, basically, what genes have been basically activated or muted by this drug. And one of my students and colleagues, Charlotte Boone, has been working a lot on this and has been getting some exciting results. And her modus operandi, if you want, was to use those ICNNs, those input convex neural networks, to try to figure out a potential. I'm not going to go into the details of how that estimation pipeline works, but it's a bit cumbersome because it requires parameterizing f theta, those potential functions, as input convex neural networks, a specific type of neural networks. But once this is optimized, then the answer is, okay, the map is just simply the grad of f theta star. One of the caveats of this approach, and as people that know about optimal transport know that this is a big caveat in OT, is that usually optimal transport has to pay a price of the curse of dimensionality. Joan was mentioning the curse of dimensionality. As practitioners, usually we try to forget it a bit, but we realize very quickly that we don't have enough samples to get a good notion of map. So what most people do in this genomics / optimal transport community is to take the measurements, 35,000, do some PCA, 250, and then run optimal transport. So what we did, and this is a bit of math, sorry, but I will try to parse it out for you. What we try to do is something different, where we try to estimate optimal transport in the original space. So we are going to do something that anyone in optimal transport theory will tell you doesn't work. And the way we are going to do it is by just going back to the book and parsing some of the most fundamental results in the theory. So what the theory tells you is that there is an optimal transport map, T star, and I'm going to use a class of costs which is known as, which is called translation invariant costs. The squared Euclidean distance is translation invariant. Most of the costs that we use between vectors are translation invariant. So I'm going to call it h of x minus tx, and then this is what I was doing before. Actually, what I was doing before is considering that h was a squared Euclidean norm. So the theory tells you that if you take a pair of dual potential functions, f star and g star, using your data, so let's, for now, suppose this is done by Odds-Jacks or by other packages, then the optimal transport is equal to x minus grad of h star, this is the Legendre transform of h, applied to grad of f star, this is the best dual potential. So this is the most fundamental and beautiful theorem in optimal transport. If you want to know more about it, very happy to chat with you after the talk. So what we realized is that, well, this part is easy now to get with Odds-Jacks. We can get some access to an estimation of this good thing. And this is also something that's easy to instantiate in Jacks. If you give me h, I can try to find h star, and then I will try to apply those things. So this is like Jacks grad of Legendre transform, Jacks grad of f applied to x. Now what we did is the following. The paper is called Monge, Bregman, Occam, because it kind of blends together ideas from sparsity and optimal transport. So how did we do this? Well, the first thing is we have, as I just told you, we have some estimators for this f star. I will call it f hat. And this is what the estimator looks like. It's a sum of weighted points, which are the grad of h computed here. And the reason why we call this Bregman is because it turns out that if you take the grad of h star of a sum of a convex combination of grad of h of zi's, this is called the Bregman centroid, or Bregman barycenter. This is just a parenthesis. Now here is the interesting part. What we try to do is what happens if you change the cost, the transportation cost in an optimal transport problem. And remember, the very first slides I was showing you, the natural distance, natural cost was just simply this distance, the L2 distance. And what we try to say is that what happens if you add to this squared norm a function tau of x, okay, of the difference, then it turns out that the grad of h star is equal to the proximal operator of this function tau. And Joan was also mentioning to the golden days of sparsity between 2010 and 2020, where this was all the craze in stats and math. Well, this is probably one of the areas where if you were born before 1990, you know everything about proximal operators. But so there's lots of things that are known about those proximal operators. And so what happens when you use them is the following. Here is an optimal transport estimation of this yellowish thing to those blue things. This is what you would expect, and actually we compute this, and this is what we recover, where it tells you, well, those points have to go in those directions like this. What happens when you start using this distance, which adds an L1 norm, is that you start seeing some displacements, some arrows that are sparse. So of course in 2D doesn't make much, it's not very impactful. In 2D, an arrow that is a sparse support is basically either going up or to the right, or down or to the left. But this is what we start seeing. And we can start also using different notion of, as I just said, there's probably 1,000 papers on computing proximal operators in the literature. And so we started basically testing and playing with a lot of different sparsifying operators. So long story short, what this model does is it tells you, I have 2 point clouds. I will try to find a map that goes from one to the other. But if I am in dimension, let's say 50,000, I am going only to select 100 variables that will move the particles from one to the next. And so this is very useful in genomics, because what we get now is we have an interpretable notion of Monge map. Because the Monge map, let's say from here, this is only, I won't have time to process those results, but what this will tell you is that a cell that was in the state before giving the medication and after the medication will just basically you will explain this transfer by just using, let's say, 100 genes that have been activated or muted at that point in time. So what we did was run some experiments, and this seems to be useful. The other thing that I really wanted to really very briefly mention, I'm not sure how much time I have left. 1 minute, 5 minutes? Great. Is, again, on the same topic, is trying to compute optimal transport maps. And as I told you earlier, if you are in a simple setting, now that you remember this formula, if you are in a simple setting where H is a squared Euclidean norm, everything translates to this transport function must be the gradient of a convex function, hence let's optimize with convex neural networks. If you've ever played with convex neural networks, you know that they're quite tedious to optimize because they have a lot of constraints in their weights. There's lots of constraints also in the architecture, and so although they have been used in the last 2 or 3 years extensively, anyone that uses them will tell you that it's actually tough to play with them. So what we're encoding using input convex neural networks is some form of good thing that looks like an optimal transport map. So what we tried to do with Theo was instead to propose a regularizer that tries to encode with something that is either 0 when it's the good thing or larger when it's the bad thing, whether it is an optimal transport map. And let me try to give you maybe a bit of intuition of how this works. Imagine I have a function f that takes a vector in and puts a vector out. So this is x1, x2, x3, x4, let's say. Those are the input vectors. I apply f. F is my black arrows. So f of x1 is here, f of x2 comes here, f of x3 comes there, and f of x4 comes there. And I just want to figure out whether that looks like an optimal transport. It's not too difficult to figure out whether that looks like an optimal transport. How would you do this? Well, you just take the same points, the green points, you look at what the distribution of the blue points, the target point is, you compute the Wasserstein distance, which is the optimal way, of mapping the green to the blue, and you compare those two objective functions. Either you got it right, so this is the case, for instance, x1 to x1, x4 to x4, or you were able to do something better, which is the optimal transport. And here, this is the case. The optimal transport T star is sending x2 to x of x3 and x3 to f of x2. And so you have a difference, if you want, between the objectives. So we call this the Morse gap. And what we do is instead of optimizing, trying to find a good optimal transport network that is convex or other properties, we just throw in that regularizer, this Morse gap, in the estimation. And what we show is that it actually recovers fairly natural things. So in this toy example, we're trying to map this red to blue, and this is blue to green, and the red is out of sample points. And if you train a neural network, an MLP, let's say, that takes a vector in and outputs a vector out, and you try to learn to train an MLP to recover this measure here from this measure, you get something. The MLP will overfit, so it will always be able to find something that transports those blue points to something that looks like this, the red point. But if you throw in this Morse gap, you start having a lot more regularity. And in particular, it's known that the optimal transport map between two sets of points, when the cost is the distance, cannot have lines that cross. This is very intuitive, because if you have two lines that cross, it's easy to unfold them. This is like called the Morse matter shortening principle. And here we were very happy to see that just simply throwing that Morse gap in there is able to recover this measure, but also is working a bit harder to enforce this without us, of course, encoding it. And we're also very happy to see that this Morse gap approach is better, much better than ICNNs in some of the genomics tasks that I described. It's also a bit better, so it helps, than the MLP. So it's a very competitive baseline. It seems to be somewhere in the middle between something that is a bit too inspired by math, which is this input convex neural network, and something that is a bit too free and not informed by math, which is just running an MLP and wait for error to decrease. So to sum up, I think we're at the point where optimal transport is actually now sitting solidly on a base of computations that scale, or we're making efforts towards that. And as a result, we're able to be a bit more creative for modeling. And so this was an illustration there with those sparse Monge maps. And I was not able to talk with some links with very exciting areas, such as generative models. You've probably heard about Wasserstein-Ganz. Martin is there. Diffusion models, Schrödinger bridges is also a very hot topic recently. And it's also related to theory and PDEs through JKO flows. So if you're interested in this, please don't hesitate to come and have a chat with me. Thank you.
Questions?
Great talk. Nice to see you, Marco. So I have a question regarding the, I guess more of a high-level question about optimal transport. So it always is looking at one transport, right, from one space into another. And I'm wondering if there's any work where you, for instance, have two steps. So for instance, going from one metric space to another metric space into another. And so now you're trying to find this map that is moving the same points in a consistent way, but you have extra bit information in the middle and perhaps even more.
Yeah, so maybe this is what you're referring to. Some people have called this Wasserstein splines. So indeed, you have like several, measures that you want to go through a smooth, map. There's also this. So the very last thing about JKO, PDEs is like a time series of probability measures, and so JKO kind of formalizes this. So there are tools. I would say that we're not there yet. We have papers on this, but it's not implemented. So that some end user in reinforcement learning, for instance, right now immediately could use it. Of course, as a researcher, you might be tempted to implement it, but our goal is to make it easier for you to use it. So.
No more questions? No? Okay. Okay, thank you. We have a small announcement that Enzo is going to do about the practicals. Thanks, Marco. Thank you, Marco.
Okay. Well, we finished with Marco's talk, the session for the afternoon, and now we have the practicals. So some comments about that. There are two practicals you have already registered, I guess, for those who want to attend. One is building ML in an open and collaborative way with the Hugging Face ecosystem. This is going to be in room 401 of the engineering building. So this is the other building. Now I will show you a plan on how to get there. And then there is the practical and introductions to JAX that is going to be room 312. There are the instructions of how to get there. So just a small map that here Steph prepared. Where is this? You can see up there, yeah. Here it is. So this is the map. Here is where we are. Here is where we had lunch. So you just keep walking through here and you get to the main building. And one of the practicals is on third floor, the other one is on for the fourth floor, okay? And that's all for today. We are seeing you tomorrow at 8:30, right? So yeah, try to be in time. Thanks.